Welcome to Heavenly Sleep Stories, the place where curiosity meets calm and knowledge gently guides you into a world of relaxation. In today's video, we invite you on a peaceful journey across our incredible solar system, a quiet exploration filled with 150 fascinating facts that will help you unwind, clear your mind, and drift effortlessly toward deep sleep. As you listen, you'll discover amazing details about every planet, moon, and mysterious region that surrounds our Sun. From the blazing storms of Jupiter to the frozen plains of Pluto, from the glowing auroras of Neptune to the ancient geology of Mars, each fact is crafted to expand your imagination while keeping your mind relaxed and at ease. This video is designed to be soft, slow, and soothing, perfect for studying, resting, meditating, or simply falling asleep to gentle cosmic knowledge. Whether you're passionate about space or just love calming facts, this journey will take you through the wonders of our cosmic neighborhood in a peaceful, comforting way. If you enjoy content that helps you relax, sleep better, and learn something new every night, don't forget to subscribe to Heavenly Sleep Stories. Your support helps us create more calming adventures, more bedtime stories for the curious mind, and more relaxing explorations of the universe. Now, get comfortable, breathe slowly, and let's begin our quiet voyage through the solar system. Fact 1. The Sun contains most solar mass. The Sun contains more than 99% of the total mass of our solar system, making it the dominant gravitational force that controls every orbiting body around it. Its enormous mass generates the heat and light necessary to sustain life on Earth, while also influencing the paths of planets, moons, asteroids, and comets. Scientists estimate that the Sun's mass is about 330,000 times greater than the mass of Earth, which demonstrates just how powerful and massive this star truly is. Its gravitational pull is so strong that even objects far out beyond Neptune remain bound to it. Although the Sun seems constant and stable, it is constantly undergoing nuclear fusion at its core, converting hydrogen into helium and releasing immense energy. This energy eventually reaches Earth as sunlight, making life possible. Understanding the Sun's mass also helps astronomers study the formation and evolution of the entire solar system. Fact 2. Mercury has extremely rapid temperature changes. Mercury experiences some of the most dramatic temperature swings in the solar system due to its lack of a significant atmosphere to trap heat. During the daytime, temperatures can soar to around 430 degrees Celsius, making its surface hotter than an oven. Yet when night falls, temperatures can plummet to approximately -180 degrees Celsius. These extreme shifts happen because Mercury rotates slowly and cannot retain heat. Its proximity to the Sun also contributes to the intense daytime heat, while its thin exosphere provides almost no insulation. Scientists study Mercury's temperature fluctuations to better understand how atmospheres regulate climate and surface conditions on rocky planets. The planet's harsh temperature environment also gives clues about its internal structure, surface composition, and the history of solar radiation in our inner solar system. Fact 3. Venus rotates backwards unlike Earth. Venus rotates in the opposite direction compared to most planets in the solar system, meaning the Sun rises in the west and sets in the east. This unusual rotation is known as retrograde rotation and is believed to have been caused by a massive collision early in the planet's history, which may have flipped its rotation entirely. Venus also rotates extremely slowly, taking about 243 Earth days to complete a single spin, making a day on Venus longer than its year. Scientists find Venus rotation fascinating because it helps them understand how violent impacts shaped our early solar system. The planet's thick clouds and intense greenhouse atmosphere further complicate its rotation patterns and contribute to the extreme weather conditions found on its surface. Fact 4. Earth is the only known watery planet. Earth remains the only confirmed planet with large, stable bodies of liquid water on its surface, a feature essential for life as we know it. Our oceans cover more than 70% of the planet's surface, creating a unique environment that moderates temperature, supports ecosystems, and cycles nutrients. Scientists believe Earth's water arrived from ancient volcanic activity combined with icy bodies that collided with the early planet. Water plays a crucial role in shaping continents, climate, and biological processes. While Mars and several moons show signs of past or hidden water, Earth remains unparalleled in its ability to maintain oceans for billions of years. Fact 5. Mars hosts the tallest volcano ever. Mars is home to Olympus Mons, the tallest volcano and tallest known mountain in the entire solar system. Standing at around 22 kilometers high, it towers nearly 3 times the height of Mount Everest. Olympus Mons is a massive shield volcano formed by repeated lava flows that spread widely instead of building steep slopes. Mars' lower gravity and lack of tectonic plate movement allowed the volcano to grow to its enormous size. Although currently inactive, Olympus Mons provides valuable insights into volcanic activity on other planets and helps scientists understand how different environments can shape planetary features over millions of years. Fact 6. Jupiter's red spot is a storm. The Great Red Spot on Jupiter is a gigantic storm that has been raging for centuries. This swirling, oval-shaped storm is large enough to fit several Earths inside it. Winds inside the red spot can reach tremendous speeds, creating powerful vortices that constantly rotate. Although the storm has been shrinking in recent decades, scientists continue to monitor it to understand atmospheric dynamics on gas giants. The red spot's striking red color is still not fully understood, but theories suggest chemical reactions caused by sunlight interacting with Jupiter's gases. Studying this storm helps researchers learn how massive atmospheres behave under extreme conditions. Fact 7. Saturn's rings are mostly icy particles. Saturn's rings are composed primarily of countless icy particles ranging from tiny grains to large chunks the size of mountains. These particles reflect sunlight beautifully, giving Saturn its iconic bright, shimmering appearance. The rings are relatively thin despite their large diameter, and they contain gaps shaped by the gravitational influence of Saturn's moons. Scientists believe the rings may be remnants of comets, asteroids, or broken moons. Their detailed structure helps astronomers understand how gravity shapes disks, including those that form planets around young stars. Fact 8. Uranus rotates sideways in space. Uranus is unique because it rotates almost entirely on its side, with an axial tilt of about 98 degrees. This unusual tilt means that each pole experiences decades of continuous sunlight followed by decades of darkness. The extreme tilt is likely the result of a colossal collision early in Uranus history. The sideways rotation affects the planet's seasons, atmosphere, and weather patterns. Uranus' unusual orientation offers clues about the chaotic and violent past of our solar system. Fact 9. Neptune has the strongest winds known. Neptune hosts the fastest and most powerful winds in the entire solar system, with speeds reaching over 2,000 kilometers per hour. These winds create massive storms and dark spots that move across the planet. Neptune's distance from the Sun means it receives little solar energy, so scientists are still exploring what drives such extreme atmospheric activity. The planet's internal heat likely contributes to these supersonic winds. Understanding Neptune's atmosphere helps researchers study extreme weather conditions on distant planets and exoplanets. Fact 10. Pluto has a heart-shaped region. Pluto features a large, bright, heart-shaped area known as Tombor Regio, named after the astronomer who discovered the dwarf planet. This region is composed largely of nitrogen ice and displays fascinating geological activity, including slowly shifting glacier. The heart shape captured global attention when NASA's New Horizons spacecraft sent back detailed images in 2015. The region provides essential clues about Pluto's climate, composition, and internal heat. Scientists continue to study this iconic feature to understand how even small, distant worlds can remain geologically active. Fact 11. The Sun is a yellow dwarf. The Sun is classified as a yellow dwarf star, a G-type main sequence star that produces steady energy through nuclear fusion, converting hydrogen into helium deep in its core. Despite the name dwarf, it is larger and more massive than most stars in the Milky Way, providing the gravitational anchor that keeps every planet, moon, asteroid, and comet in stable orbit. Its light appears yellow from Earth because our atmosphere scatters shorter wavelengths, though in space the Sun shines pure white. Without the Sun's constant energy, Earth would be frozen and lifeless, as its radiation drives weather patterns, seasons, plant growth, and the delicate balance required for liquid water. The Sun is about 4.6 billion years old and is roughly halfway through its life cycle, meaning humanity lives during its most stable evolutionary stage. Solar activity, such as sunspots and solar flares, can influence satellites, power grids, and communication systems, showing how interconnected we are with this distant yet essential star. Even though it is incredibly massive and powerful, the Sun is only one of hundreds of billions of stars in our galaxy, and studying it helps scientists better understand the life cycles of stars across the universe. Fact 12. Mercury has no real atmosphere. Mercury does not have a true atmosphere, only a thin and unstable exosphere made of scattered particles that escape quickly into space. Because it lacks atmospheric pressure, temperatures swing wildly from extreme heat during the day to severe cold at night. With no air to trap heat or block harmful radiation, the surface is constantly exposed to solar wind and cosmic rays, resulting in a heavily cratered and ancient landscape. Mercury's exosphere contains trace amounts of oxygen, sodium, hydrogen, helium, and potassium. But these particles are so sparse they cannot create clouds, weather, or breathable air. The planet's proximity to the Sun intensifies its harsh environment, bombarding the surface with intense sunlight and high-energy particles. Without an atmosphere, sound cannot travel on Mercury, making it an entirely silent world. Its inability to hold onto gases is connected to its small size, weak gravity, and scorching temperatures. By studying Mercury, scientists gain insight into how atmospheres evolve and disappear over time, which may help us understand the early history of Earth and other rocky planets. Despite its harsh environment, Mercury remains an important object for planetary research. Fact 13. Venus is hotter than Mercury. Venus is the hottest planet in the solar system, even though Mercury is closer to the Sun, because Venus has a thick and toxic atmosphere made mostly of carbon dioxide. This atmosphere creates an extreme greenhouse effect, trapping heat so effectively that surface temperatures reach levels hot enough to melt lead. Its clouds are made of sulfuric acid, reflecting sunlight but also keeping heat sealed in, creating an environment with crushing pressure over 90 times greater than Earth's. Venus rotates extremely slowly and in the opposite direction of most planets, causing its day to be longer than its year. The combination of slow rotation and greenhouse heating leads to an atmosphere that circulates heat evenly around the planet, making both day and night sides equally scorching. No spacecraft has survived on the surface for long due to the extreme temperature and pressure, which destroy electronics in minutes or hours. Studying Venus helps scientists understand runaway greenhouse effects, atmospheric chemistry, and climate evolution, providing insight into what could happen to Earth under extreme conditions. Despite being Earth's twin in size and composition, Venus is one of the most hostile worlds ever discovered. Fact 14. Earth's moon stabilizes our tilt. Earth's moon plays a critical role in stabilizing our planet's axial tilt, which is responsible for the seasons and long-term climate patterns. Without the moon's gravitational influence, Earth's tilt would vary wildly over millions of years, causing unpredictable climate swings that could make life far more difficult. The moon's stabilizing effect keeps Earth's tilt steady at about 23.5 degrees, ensuring relatively consistent seasonal cycles. The moon also slows Earth's rotation through tidal interactions, gradually increasing the length of our day over billions of years. Tides produced by the moon-shaped coastlines support marine ecosystems and influence ocean circulation. The moon formed around 4.5 billion years ago, likely from debris produced after a massive collision between early Earth and a Mars-sized object. This event created a unique Earth-Moon system unlike most seen elsewhere in the solar system. Without the moon, Earth's climate might have been too unstable for complex life to develop. The moon also protects Earth by absorbing impacts from asteroids and comets that might otherwise threaten life. Its importance extends far beyond lighting the night sky. It has shaped Earth's evolution from the very beginning. Fact 15. Mars once had flowing rivers. Mars once had flowing rivers, lakes, and possibly even large oceans, as shown by dried riverbeds, mineral deposits, and erosion patterns scattered across its surface. Billions of years ago, the planet was warmer and wetter, with a thicker atmosphere that allowed liquid water to remain stable. Evidence from orbiters and rovers shows that ancient Mars supported long-term water activity, meaning it may have once hosted conditions suitable for microbial life. Over time, the planet lost most of its atmosphere due to solar wind stripping and its weak magnetic field, causing temperatures to drop and water to freeze underground or evaporate into space. Today, Mars is a cold and dry desert, but traces of water ice remain at the poles and possibly underground. Studying Mars helps scientists understand how planetary environments change and whether life could exist elsewhere. The presence of water-related minerals like clays and sulfides confirms that Mars had a much more Earth-like climate in the past. These discoveries fuel exploration missions searching for signs of ancient life and clues about the planet's transformation over billions of years. Fact 16. Jupiter has dozens of moons. Jupiter has dozens of moons, with over 90 confirmed natural satellites orbiting the giant planet. These moons range from tiny asteroid-sized bodies to massive worlds like Ganymede, the largest moon in the solar system. Jupiter's strong gravity captures and holds many objects, forming a complex and diverse system that resembles a miniature solar system. Some of its moons, such as Europa, may harbor subsurface oceans beneath icy crusts, raising the possibility of extraterrestrial life. Io, another major moon, is the most volcanically active body in the solar system, with constant eruptions driven by Jupiter's tidal forces. Ganymede even has its own magnetic field, a rare feature for a moon. Studying Jupiter's moons helps scientists understand how planets and satellites form and evolve over time. The variety of surface features, geological activity, and potential habitats makes Jupiter's moon system one of the most exciting regions in planetary science. Each moon tells a different story about the history of the solar system. Fact 17. Saturn could float on water. Saturn could float on water because its average density is lower than that of liquid water, making it the least dense planet in the solar system. Despite its massive size, Saturn is composed mostly of hydrogen and helium, extremely light gases that reduce its overall density. If a giant cosmic ocean large enough existed, Saturn would theoretically float like a massive celestial balloon. Its low density is a result of its composition and internal structure, with heavier elements concentrated deep in the core. Saturn's appearance is dominated by its iconic rings, made of ice, rock, and dust particles that stretch thousands of kilometers but are incredibly thin. The planet's strong winds and storms create banded cloud patterns across its surface. Studying Saturn helps scientists learn about gas giant formation, atmospheric chemistry, and the dynamics of ring systems. Its unusual density makes it one of the most fascinating planets in the solar system. Fact 18. Uranus has faint dusty rings. Uranus has faint dusty rings that are much darker and more subtle than the bright rings of Saturn. These rings are composed of small particles made of rock and carbon-rich material, giving them a dark appearance. Uranus has 13 known rings, which were discovered in 1977 when scientists observed how the planet blocked light from a distant star. The rings are narrow, uneven, and likely formed from shattered moons or captured debris. Uranus rotates on its side, tilted at about 98 degrees, causing its rings and moons to orbit in an unusual sideways orientation. This extreme tilt creates dramatic seasonal changes that last decades. The planet's faint rings offer clues about collisions, gravitational interactions, and the evolution of planetary systems. Despite being difficult to observe, they remain one of the most intriguing features of Uranus. Fact 19. Neptune appears vivid deep blue. Neptune appears vivid deep blue due to the presence of methane in its atmosphere, which absorbs red light and reflects blue wavelengths back into space. Its color is even more intense than Uranus, suggesting additional atmospheric components or cloud patterns enhance its deep blue shade. Neptune is the windiest planet in the solar system, with winds reaching extreme speeds that shape its swirling storms and cloud structures. The planet's distant location makes it cold and dim, yet it remains surprisingly active. Its great dark spot, a massive storm system, resembles Jupiter's Great Red Spot but appears and disappears over time. Studying Neptune helps scientists understand atmospheric dynamics, ice giant chemistry, and the behavior of planets far from their stars. Its striking blue hue makes Neptune one of the most visually captivating worlds. Fact 20. Pluto's surface contains frozen nitrogen. Pluto's surface contains frozen nitrogen along with methane and carbon monoxide ices, creating bright plains and dark patches shaped by seasonal changes. Its heart-shaped region, called Tombor Regio, is made of vast nitrogen ice that slowly shifts and flows like glacier on Earth. Even though Pluto is extremely cold, its surface is geologically active, showing mountains, valleys, and smooth plains that suggest internal heat once existed. The thin atmosphere made of nitrogen expands and collapses as Pluto moves along its long, elliptical orbit. Pluto's unique combination of ices gives it a constantly changing appearance. Studying Pluto reveals how small icy worlds form and evolve at the outer edges of the solar system. Fact 21. The solar system is 4.6 billion. The solar system is approximately 4.6 billion years old, forming from a massive cloud of gas and dust known as the solar nebula. Over time, gravity pulled the material inward, creating a spinning disk with the Sun forming at the center. The leftover material gradually clumped together, forming planets, moons, asteroids, and comets. Evidence for this age comes from radiometric dating of meteorites, which contain some of the oldest unchanged material in the solar system. The early solar system was chaotic, with countless collisions shaping the growing planets and distributing heavy elements across space. This violent period produced features such as the Moon, which formed after a giant impact between early Earth and a Mars-sized body. Understanding the solar system's age helps scientists trace the timeline of planetary evolution, climate changes, and the conditions under which life emerged on Earth. Over billions of years, the solar system has settled into a stable configuration, but it still continues to evolve through slow orbital shifts, impacts, and solar changes. Knowing its age helps us place humanity's existence in a much larger cosmic context, showing how young life on Earth truly is compared to the ancient history of our planetary neighborhood. Fact 22. The Sun's gravity controls everything. The Sun's gravity controls everything in the solar system, acting as the central force that keeps every planet, moon, asteroid, and comet in orbit. This immense gravitational pull extends far beyond the planets, influencing distant objects in the Kuiper Belt and even the faraway Oort Cloud. Without the Sun's gravity, the solar system would disperse into space, and Earth would drift away into darkness and freeze. The Sun contains over 99% of all mass in the solar system, giving it unmatched gravitational dominance. Its gravity shapes orbital speeds, governs seasons, and determines the stability of long-term planetary motion. Gravity also drives the solar wind, which interacts with planetary magnetic fields and atmospheres. Even though the Sun is incredibly massive, its gravity remains perfectly balanced with the orbital motion of the planets, preventing them from falling inward or spinning away. Studying the Sun's gravitational influence helps scientists understand orbital mechanics, planetary formation, and the long-term evolution of planetary systems. The Sun's gravity is the invisible structure that holds everything together, maintaining order in a system that would otherwise be chaotic. Fact 23. Mercury orbits the Sun fastest. Mercury orbits the Sun faster than any other planet, completing one full revolution in just 88 Earth days. Its rapid orbit is a direct result of its proximity to the Sun, where gravitational force is strongest. Because Mercury moves so quickly, it experiences extreme temperature differences between day and night, and its sunrise to sunrise day is actually longer than its year. Its elliptical orbit also causes the Sun to appear dramatically larger and move oddly in Mercury's sky. Mercury's fast orbit helped confirm Einstein's theory of general relativity, as scientists observed small deviations in its motion that older models could not explain. This planet's rapid trip around the Sun provides insight into how gravity affects orbital speeds and energy. Even though Mercury is small and airless, its fast orbit makes it a unique world in the solar system's dynamic structure. Fact 24. Venus has crushing atmospheric pressure. Venus has crushing atmospheric pressure over 90 times greater than Earth's, making its surface environment similar to being nearly a kilometer underwater. This intense pressure is caused by its thick carbon dioxide atmosphere, which traps heat and creates a runaway greenhouse effect. The dense atmosphere also contains clouds of sulfuric acid, adding to the planet's extreme conditions. Any spacecraft attempting to land on Venus must withstand enormous pressure and heat, and most have survived only a short time before being destroyed. The pressure shapes Venus's geology, influencing volcanic activity and the planet's slow rotational dynamics. Understanding Venus's atmosphere helps scientists study climate change, atmospheric chemistry, and the long-term evolution of rocky planets. Despite being similar to Earth in size, Venus is one of the most hostile places in the solar system. Fact 25. Earth's magnetic field protects life. Earth's magnetic field protects life by deflecting harmful solar radiation and charged particles from the Sun. This magnetic shield is generated by the movement of molten iron in Earth's outer core, creating a powerful dynamo that extends far into space. Without this protective field, the atmosphere would gradually be stripped away by solar wind, and the surface would be exposed to dangerous levels of radiation. The magnetic field also shapes auroras, the stunning light displays near Earth's poles caused by charged particles interacting with the atmosphere. Over time, the magnetic field shifts, drifts, and even reverses, but continues to protect life regardless of its orientation. Studying Earth's magnetosphere helps scientists understand how planets maintain atmospheres and support habitability. This invisible shield is one of the key reasons Earth can sustain complex life. Fact 26. Mars has giant dust storms. Mars has giant dust storms that can grow large enough to cover the entire planet. These storms are driven by sunlight heating the surface, which creates rising air currents that lift fine dust particles into the atmosphere. Once airborne, the dust can remain suspended for months, blocking sunlight and dramatically reducing surface temperatures. Planet-wide storms can disrupt spacecraft operations and temporarily obscure surface features from telescopes. The dust itself is extremely fine and can cling to equipment, posing challenges for rovers and future human missions. Mars experiences these storms regularly due to its thin atmosphere, which allows dust to travel long distances with minimal resistance. Scientists study Martian dust storms to better understand climate patterns, atmospheric dynamics, and the challenges of exploring the red planet. Despite being smaller than Earth, Mars can produce storms on a scale unmatched in its intensity and global reach. Fact 27. Jupiter emits more heat internally. Jupiter emits more heat internally than it receives from the Sun, due to the slow gravitational contraction of its massive atmosphere. This process, known as the Kelvin-Helmholtz mechanism, releases energy as the planet's interior compresses over time. As a result, Jupiter radiates almost twice as much heat as it absorbs from sunlight. This internal heat drives powerful storms, fast winds, and the dynamic cloud patterns visible in its atmosphere. The famous Great Red Spot, a storm larger than Earth, is sustained in part by this internal energy. Jupiter's internal heating also influences the environment around its moons, shaping volcanic activity on Io and potentially helping maintain subsurface oceans on Europa and Ganymede. Studying Jupiter's heat output helps scientists understand gas giant formation, atmospheric physics, and the evolution of massive planets both in and beyond our solar system. Fact 28. Saturn's rings are surprisingly thin. Saturn's rings are surprisingly thin, often only about 10 meters thick despite stretching hundreds of thousands of kilometers across. These rings are made of countless particles of ice and rock that range in size from tiny grains to large chunks. Their extreme thinness is due to the planet's gravitational forces, which cause ring particles to settle into a narrow, flattened plane. The rings may be relatively young compared to the planet itself, possibly formed from shattered moons or captured comets. Although they appear solid from a distance, the rings are mostly empty space with particles orbiting in carefully balanced paths. Saturn's rings provide valuable insights into disk formation, orbital dynamics, and the processes that shape planetary systems. Their delicate structure makes them one of the most iconic and visually stunning features of the solar system. Fact 29. Uranus was discovered accidentally. Uranus was discovered accidentally in 1781 by astronomer William Herschel, who initially believed it was a comet or a distant star. Its slow movement across the sky revealed it was actually a new planet, making Uranus the first planet discovered with a telescope. This discovery expanded the known boundaries of the solar system and changed our understanding of its structure. Uranus's unusual tilt, which causes it to rotate on its side, remains one of its most fascinating features. The planet's discovery inspired further searches that later led to the identification of Neptune. Uranus's accidental discovery highlights the importance of careful observation and curiosity in scientific breakthroughs, showing how unexpected findings can reshape our view of the universe. Fact 30. Neptune was predicted mathematically. Neptune was predicted mathematically before it was ever seen through a telescope. Astronomers noticed irregularities in Uranus's orbit that suggested a hidden planet was influencing it through gravitational pull. Using mathematical calculations, scientists such as Urbain Le Verrier and John Couch Adams independently predicted the location of the unknown planet with remarkable accuracy. When astronomers pointed a telescope at the predicted spot in 1846, Neptune was found almost exactly where the calculations indicated. This discovery was a triumph of physics and mathematics, proving that unseen celestial bodies could be detected through their gravitational effects alone. Neptune's prediction and discovery marked a milestone in astronomy, showcasing the power of scientific reasoning and precision. Fact 31. Pluto has 5 known moons. Pluto has 5 known moons, with Charon being the largest and most significant due to its size relative to Pluto. Charon is so large, about half Pluto's diameter, that the two bodies actually orbit a common center of gravity located outside Pluto's surface, making them a unique binary system. The other moons, Nix, Hydra, Kerberos, and Styx, are much smaller and irregularly shaped, likely formed from debris after a massive collision early in Pluto's history. These moons reflect sunlight differently, suggesting diverse surface compositions and histories. Their orbits are surprisingly stable despite their chaotic shapes and small sizes. Studying Pluto's moons helps scientists understand how dwarf planets evolve, how collisions shape small bodies, and why some distant objects form complex multi-moon systems. The Pluto system remains one of the most fascinating discoveries from NASA's New Horizons mission, revealing a surprisingly dynamic world far beyond Neptune. Fact 32. The Kuiper Belt surrounds Neptune. The Kuiper Belt surrounds Neptune's orbit and stretches far beyond it, forming a vast ring of icy objects similar to the asteroid belt but much larger and more massive. This region contains dwarf planets like Pluto, Haumea, and Makemake, as well as countless smaller icy bodies believed to be remnants from the solar system's formation. The Kuiper Belt is a cosmic fossil zone, preserving materials that have barely changed in billions of years. Its objects are composed primarily of ice, frozen gases, and rock, offering clues about the early solar nebula. Neptune's gravity plays a major role in shaping the distribution and orbits of Kuiper Belt objects, creating regions of resonance where objects remain in stable orbits for long periods. Studying the Kuiper Belt helps scientists explore how planets formed and how giant planets migrated in the early solar system. This distant region remains one of astronomy's most mysterious frontiers. Fact 33. The Oort Cloud is hypothetical. The Oort Cloud is a hypothetical, distant spherical shell of icy objects surrounding the solar system, believed to extend nearly a light-year from the Sun. Although it has never been directly observed, strong evidence for its existence comes from the trajectories of long-period comets that enter the inner solar system from extremely distant regions. These comets appear to originate from a vast reservoir of icy bodies disturbed occasionally by passing stars or galactic tides. The Oort Cloud is thought to contain trillions of objects left over from the early formation of the planets, ejected outward by gravitational interactions with Jupiter and Saturn. Understanding the Oort Cloud helps scientists model the solar system's boundary and its interactions with the Milky Way. It also serves as a reminder that the solar system is far larger and more complex than the regions we have explored directly. Fact 34. Comets originate from far distances. Comets originate from far distances, with short-period comets typically coming from the Kuiper Belt and long-period comets arriving from the distant Oort Cloud. These icy bodies contain frozen gases, dust, and organic materials preserved since the solar system's formation. When a comet approaches the Sun, its ice vaporizes, forming a glowing coma and a tail that always points away from the Sun due to the solar wind. Comets can reveal information about the early solar system, including its chemistry and the conditions that existed 4.6 billion years ago. Their unpredictable paths and stunning appearances have fascinated civilizations throughout history. Scientists continue to study comets to understand planetary formation, the delivery of water and organics to Earth, and the forces shaping the solar system's outer edges. Fact 35. Meteors burn entering Earth's atmosphere. Meteors burn entering Earth's atmosphere due to intense friction with air molecules, causing them to heat up and create a bright streak across the sky. Most meteors are tiny, often smaller than a grain of sand, and disintegrate completely before reaching the ground. The air in front of the meteor compresses so rapidly that it heats to thousands of degrees, producing the familiar glow and sometimes a trail of ionized gas. Larger meteors can survive the journey, reaching the ground as meteorites that provide valuable scientific clues about asteroids and early planetary material. Meteor showers occur when Earth passes through debris left by comets or asteroids, creating predictable events like the Perseids and Leonids. Studying meteors helps scientists understand the composition of small celestial bodies and the long-term evolution of debris in the solar system. Fact 36. Mercury's day is longer than year. Mercury's day is longer than its year, meaning it takes more time to rotate once on its axis than to complete an orbit around the Sun. A single rotation lasts about 59 Earth days, while its orbit takes only 88 Earth days. This unusual rhythm creates a strange day-night cycle where the Sun appears to pause, reverse direction, and then continue across Mercury's sky due to orbital and rotational interactions. The slow rotation combined with Mercury's thin exosphere contributes to the planet's extreme temperature swings. Scientists study Mercury's rotation to understand tidal locking, orbital mechanics, and how gravitational interactions with the Sun shaped its motion. Mercury's unique timing makes it one of the most fascinating rocky planets in the solar system. Fact 37. Venus experiences a runaway greenhouse. Venus experiences a runaway greenhouse effect, making it the hottest planet in the solar system despite being farther from the Sun than Mercury. Its dense carbon dioxide atmosphere traps heat so effectively that surface temperatures reach over 460 degrees Celsius. Volcanic activity likely released massive amounts of greenhouse gases early in Venus's history, overwhelming its ability to regulate climate. The thick clouds of sulfuric acid further trap infrared radiation, creating an environment inhospitable to life. Understanding Venus's runaway greenhouse helps scientists study climate evolution, atmospheric chemistry, and how planetary atmospheres can drastically change over time. Venus serves as a warning of how powerful greenhouse effects can become when feedback loops go unchecked. Fact 38. Earth has diverse life forms. Earth has diverse life forms, ranging from microscopic bacteria to complex plants, animals, and humans. This diversity is supported by Earth's unique combination of liquid water, protective atmosphere, magnetic field, and moderate climate. Life exists in nearly every environment, from deep-sea trenches to high mountain peaks, showing remarkable adaptability. Earth's biodiversity drives ecosystems, nutrient cycles, and the stability of the planet's biosphere. Scientists study life's diversity to understand evolution, environmental changes, and the delicate balance that makes Earth habitable. Compared to other planets in the solar system, Earth stands alone as the only known world to support such rich and complex life. Fact 39. Mars soil includes toxic perchlorates. Mars soil includes toxic perchlorates, chemical compounds that can be harmful to human health and complicate future colonization efforts. Perchlorates can interfere with thyroid function and become dangerous when heated, releasing oxygen and chlorine. Their presence indicates that Mars' surface chemistry is far different from Earth's, shaped by intense ultraviolet radiation and a thin atmosphere. While perchlorates pose challenges for agriculture and human missions, they may also serve as a potential resource for extracting oxygen or fuel. Scientists study these chemicals to understand Martian geochemistry, environmental hazards, and the feasibility of sustaining long-term human presence on the red planet. Fact 40. Jupiter's magnetosphere is immense. Jupiter's magnetosphere is immense, extending millions of kilometers into space and making it the largest magnetic structure in the solar system. Its magnetic field is over 20,000 times stronger than Earth's, created by the rapid rotation and metallic hydrogen deep within the planet. This magnetosphere traps charged particles, forming intense radiation belts that can damage spacecraft and affect Jupiter's moons. It also interacts with the solar wind, creating auroras far more powerful than those found on Earth. Jupiter's magnetosphere shapes the space environment around the giant planet and influences volcanic and atmospheric activity on nearby moons like Io. Understanding this massive magnetic region helps scientists explore planetary magnetism and space weather across the solar system. 41. Saturn has more than 80 moons. Saturn has over 80 confirmed moons, making it one of the most complex and fascinating planetary systems in the entire solar system. These moons range from tiny ice fragments only a few kilometers wide to large, fully developed worlds such as Titan, which has a dense atmosphere thicker than Earth's and lakes of liquid methane. Another famous moon, Enceladus, ejects plumes of water vapor from its subsurface ocean, suggesting active hydrothermal vents that may even support microbial life. The incredible variety among Saturn's moons provides astronomers with valuable insight into planetary formation, gravitational interactions, and the evolution of icy bodies. Many of these moons show evidence of resurfacing, geological activity, or interactions with Saturn's rings, which themselves may have formed from destroyed moons long ago. The study of Saturn's moon system helps scientists understand how diverse and dynamic small worlds can be, how atmospheres evolve, and how conditions necessary for life might appear in unexpected places. With each new mission and observation, Saturn's moons continue to reveal new mysteries, proving that this planet is a treasure trove of cosmic discoveries. 42. Uranus has extremely cold temperatures. Uranus is the coldest planet in the solar system, with temperatures dropping as low as -224 degrees Celsius, even colder than Neptune despite receiving more sunlight. This makes Uranus a scientific mystery because it releases almost no internal heat, unlike the other giant planets, which radiate significantly more energy than they receive. Its unusual axial tilt of about 98 degrees causes the planet to rotate on its side, leading to seasons that last over 20 years each and creating extreme changes in sunlight across its atmosphere. The atmosphere itself is composed of hydrogen, helium, and methane, the methane absorbing red light and giving Uranus its signature blue-green color. Because of its internal coldness, atmospheric processes appear strangely subdued compared to Neptune, though the planet still experiences fast winds and occasional storms. Uranus' frigid temperatures, bizarre rotation, and weak internal heat make it one of the biggest enigmas of planetary science, and future missions hope to answer major questions about its interior structure, evolution, and why it behaves so differently from the other ice giants. 43. Neptune radiates internal heat intensely. Neptune radiates far more internal heat than it receives from the Sun, a characteristic that drives some of the most extreme weather patterns in the solar system. Despite being extremely distant from the Sun, Neptune maintains dynamic atmospheric conditions powered by an internal heat source that remains poorly understood. This heat fuels massive storms, including the famous Great Dark Spot, and produces winds that can reach incredible speeds of up to 2,000 kilometers per hour, the fastest ever recorded on any planet. Neptune's deep blue color is due to methane in the atmosphere, but the vividness of the color may also involve unknown atmospheric components. The contrast between its frigid outer layers and warm interior creates turbulence that shapes its dramatic weather system. Scientists believe Neptune's internal heat may come from slow gravitational compression or leftover formation energy, but the exact mechanism remains a subject of ongoing research. Its violent storms, powerful winds, and intense internal heat make Neptune a crucial object of study for understanding ice giant dynamics and the role of internal energy in shaping planetary atmospheres. 44. Pluto's atmosphere freezes during orbit. Pluto follows a highly elliptical orbit that brings it closer to and farther from the Sun in extreme cycles, causing its thin nitrogen atmosphere to behave in dramatic ways. When Pluto travels to the farthest part of its orbit, temperatures drop so much that its atmosphere literally freezes and falls to the surface as frost, turning the planet into a world shrouded in frozen nitrogen. As Pluto moves closer to the Sun again, the nitrogen sublimates back into gas, recreating the atmosphere temporarily. This seasonal atmospheric collapse is unlike anything observed on any other planet in the solar system. Pluto's atmosphere also contains traces of methane and carbon monoxide, forming thin hazes that stretch high above its surface. These hazes are layered, suggesting complex chemical reactions driven by sunlight. The presence of glacier, sublimating ice, and shifting atmospheric density reveals that Pluto, despite being distant and cold, is a dynamic and evolving world. Its atmospheric freeze-thaw cycle is a key puzzle for scientists studying how dwarf planets change over long periods of time and how ices behave under extreme conditions. 45. The Sun fuses hydrogen constantly. The Sun is a massive nuclear fusion reactor, constantly converting hydrogen into helium in its core through a process that releases enormous amounts of energy. This energy supports life on Earth, drives the climate system, and illuminates the entire solar system. The fusion reaction in the Sun's core produces light and heat that gradually travel outward, taking tens of thousands of years to reach the surface before radiating into space. Even though the Sun consumes millions of tons of hydrogen every second, it has enough fuel to continue shining for billions of years. The stability of the Sun's fusion process is a key reason why Earth has remained habitable for such a long time. Without this constant fusion, temperatures on our planet would collapse instantly, and photosynthesis, weather, and the water cycle would cease to exist. The Sun's fusion also generates magnetic fields that interact with Earth's magnetic field, sometimes causing solar storms and auroras. Understanding solar fusion helps scientists predict solar activity, protect satellites, and better understand the life cycles of stars throughout the universe. 46. Solar flares release massive energy. Solar flares are sudden, intense bursts of energy and radiation from the Sun's surface caused by the release of magnetic energy stored in its atmosphere. These flares can release energy equivalent to billions of nuclear bombs in just a few minutes, producing X-rays, ultraviolet light, and charged particles that travel through space. When directed toward Earth, solar flares can disrupt communications, damage satellites, and even cause power grid failures. They also interact with Earth's magnetosphere to produce spectacular auroras near the poles. Solar flares are closely linked to sunspots, regions of intense magnetic activity on the Sun, and are part of the Sun's roughly 11-year activity cycle. Studying solar flares helps scientists predict space weather, protect technology in orbit, and understand the processes powering our star. Despite their destructive potential, solar flares are natural and necessary events that help release built-up energy in the Sun's atmosphere, keeping the star stable over long periods. These bursts reveal the dynamic nature of the Sun and the vast amounts of energy flowing constantly in our solar system. 47. Planetary orbits are nearly circular. Most planets in the solar system follow orbits that are nearly circular rather than highly elliptical, which contributes to the stability and predictability of their motion around the Sun. Circular orbits ensure that the distance between a planet and the Sun does not vary dramatically, which stabilizes climates and seasonal cycles, particularly on Earth. Orbital mechanics, governed by the laws of gravity described by Newton and refined by Kepler, dictate how planets travel along these paths, balancing the Sun's pull with the planet's momentum. Slight deviations from circularity, called eccentricities, explain variations in solar energy reaching the planets and the differences in seasons. Nearly circular orbits also help prevent catastrophic collisions between planets, asteroids, and other objects, maintaining the long-term structure of the solar system. Studying orbital shapes allows astronomers to predict planetary positions, understand planetary system formation, and explore exoplanets in other solar systems. The near-circular nature of orbits is a fundamental feature that defines the dynamics, climate stability, and long-term evolution of planetary systems, highlighting the precision of gravitational interactions across billions of years. 48. Asteroid belt sits between planets. The asteroid belt lies between Mars and Jupiter and contains millions of rocky bodies, ranging from tiny dust grains to dwarf planet-sized objects. These asteroids are leftover material from the early solar system that never coalesced into a planet, largely due to the strong gravitational influence of nearby Jupiter. The belt contains diverse objects, from metallic fragments to icy rocks, each providing clues about the conditions and processes during planetary formation. Asteroids occasionally collide, creating debris that travels through space, some of which enters Earth's atmosphere as meteors. Studying the asteroid belt helps scientists understand the composition of the early solar nebula, planetary migration, and potential threats to Earth from near-Earth objects. Some missions, like NASA's Dawn spacecraft, have visited asteroids such as Vesta and Ceres, revealing surface geology, internal structure, and signs of past activity. The belt is a dynamic, constantly changing region that serves as both a time capsule and a laboratory for understanding the evolution of rocky material in the solar system. 49. Earth's moon formed from collision. Earth's moon most likely formed after a massive collision between the young Earth and a Mars-sized protoplanet named Theia. This giant impact ejected huge amounts of material into orbit around Earth, which eventually coalesced into the moon. This hypothesis explains why the moon's composition is similar to Earth's mantle and why it lacks significant iron in its core. The moon stabilizes Earth's axial tilt, helping maintain relatively stable seasons, and affects ocean tides through its gravitational pull. Studying lunar rocks brought back by the Apollo missions confirmed the moon's origin and provided insight into the early solar system. The moon's formation also influenced Earth's rotation rate and may have contributed to the development of life by moderating environmental conditions. By understanding the moon's origins, scientists can learn about giant impacts on planets elsewhere and the processes that shape planetary systems across the galaxy. The moon remains a key object for exploring planetary evolution and understanding how celestial collisions shape worlds. 50. Mars has frozen polar caps. Mars has permanent polar ice caps composed of water ice and seasonal layers of frozen carbon dioxide, also called dry ice. During the Martian winter, CO freezes from the atmosphere and accumulates over the poles, creating layered deposits that expand and contract with seasonal changes. The water ice caps remain year-round, providing a crucial reservoir of frozen water and clues about Mars' climate history. Observations from orbiters and rovers have revealed that these polar regions contain layered deposits formed over millions of years, capturing information about past atmospheric conditions, dust storms, and possibly glacial flows. Understanding Mars' polar caps is essential for studying the planet's potential habitability, past liquid water, and future human exploration, as they may serve as a source of water for astronauts. Seasonal sublimation of CO also drives local wind patterns and creates unique surface features, such as polygonal cracks and frost dunes. Mars' frozen poles demonstrate the complexity and dynamism of the red planet's surface and climate, even in the absence of thick atmosphere or abundant liquid water. 51. Jupiter's moon Europa may harbor oceans. Europa, one of Jupiter's largest moons, is covered by a thick layer of ice that conceals a subsurface ocean of liquid water. Tidal heating caused by gravitational interactions with Jupiter and other Galilean moons keeps this ocean from freezing completely, creating conditions that may support microbial or even more complex life. Europa's icy crust is crisscrossed by ridges and fractures, suggesting movement and possible exchange of materials between the surface and ocean. Plumes of water vapor have been detected erupting from cracks, hinting at active geology and ocean surface interaction. Studying Europa allows scientists to understand icy world dynamics, ocean chemistry, and habitability beyond Earth. Future missions, such as NASA's Europa Clipper, aim to investigate its ice shell thickness, ocean depth, and potential biosignatures. Europa represents one of the most promising environments for life in the solar system, showing that even distant moons can harbor hidden oceans with potential for biological activity. 52. Saturn's moon Titan has methane lakes. Titan, Saturn's largest moon, is unique for having lakes and rivers of liquid methane and ethane on its surface. Its dense nitrogen-rich atmosphere and extremely cold temperatures allow hydrocarbons to exist in liquid form, creating a hydrological cycle similar to Earth's but with methane instead of water. Titan's surface features include dunes, river channels, and potential cryovolcanoes that may erupt icy materials. Studying Titan helps scientists understand prebiotic chemistry, atmospheric processes, and how organic compounds behave in extreme environments. Radar imaging from Cassini revealed vast lakes, seas, and seasonal changes in liquid distribution. Titan's methane lakes could provide clues about chemical pathways that may lead to life or complex organic molecules. Unlike Earth, Titan is a world where liquids other than water drive surface processes, demonstrating the diversity of planetary bodies and their potential for hosting unique chemical and possibly biological systems. Titan remains a prime target for exploration and the study of alien but Earth-like processes. 53. Uranus has mysterious internal heat. Unlike Neptune, Uranus emits very little internal heat, making it the coldest planet in the solar system and a unique case among the giant planets. Its interior is believed to contain icy layers mixed with rock and hydrogen compounds, but the exact mechanism explaining the lack of heat release is still debated. Some theories suggest a thermal boundary or stagnant layer inside Uranus traps heat, preventing it from escaping. Despite weak internal energy, Uranus experiences winds and atmospheric motion influenced by solar heating and rotation. Its extreme axial tilt of about 98 degrees adds complexity to seasonal variations and polar illumination, creating unusual climate dynamics. Studying Uranus' interior helps scientists compare ice giants, understand planetary evolution, and explore why seemingly similar planets can have drastically different thermal outputs. Uranus remains a mystery in planetary science, and future missions could reveal much about its composition, heat transfer mechanisms, and atmospheric behavior. 54. Neptune's moon Triton orbits backwards. Triton, Neptune's largest moon, has a retrograde orbit, meaning it moves in the opposite direction of Neptune's rotation. This unusual orbit suggests that Triton was likely captured from the Kuiper Belt rather than forming with Neptune. Its capture would have generated significant tidal heating, shaping its internal structure and possibly resurfacing the moon. Triton's surface is covered in nitrogen ice, with features such as geysers and ridges indicating active geology. The retrograde motion also makes Triton slowly spiral inward, eventually expected to break apart or collide with Neptune billions of years from now. Studying Triton's orbit, geology, and surface composition provides insights into capture mechanisms, tidal forces, and icy moon dynamics. Its unique motion and activity make it one of the most interesting moons in the solar system and a natural laboratory for understanding captured planetary bodies and the evolution of distant moons. 55. Pluto's moon Charon nearly equals size. Pluto's largest moon, Charon, is nearly half the size of Pluto, forming a binary system in which both bodies orbit a common center of gravity outside Pluto's surface. This makes their relationship unique in the solar system and affects the dynamics of the Pluto system, including tidal locking, rotation rates, and orbital interactions. Charon's surface features cliffs, canyons, and possible cryovolcanoes, revealing a geologically active past. The binary system also stabilizes Pluto's orientation and creates fascinating gravitational effects on its smaller moons. Studying Charon provides insight into dwarf planet formation, moon evolution, and tidal processes in binary systems. NASA's New Horizons mission revealed detailed images and compositions, showing a surprising complexity for a distant icy moon. Charon demonstrates how moons can be nearly equal in size to their planet, challenging traditional ideas about planet-moon relationships and revealing the diverse nature of bodies in the Kuiper Belt. 56. The Sun rotates unevenly across latitudes. The Sun rotates unevenly, with its equator completing a rotation approximately every 25 days while the poles rotate every 36 days. This phenomenon, called differential rotation, occurs because the Sun is a massive ball of plasma, not a solid body. Differential rotation stretches magnetic field lines, generating sunspots, solar flares, and coronal mass ejections. These magnetic phenomena impact space weather, satellite operations, and communication systems on Earth. Studying the Sun's uneven rotation helps scientists understand stellar magnetic cycles, the formation of solar activity, and the long-term evolution of our star. It also informs models of other stars, many of which exhibit similar rotational behavior. Differential rotation is a key factor in powering the solar dynamo, which drives the Sun's magnetic field and activity cycles. Understanding this rotation is essential to predicting solar storms and understanding the life cycle of the Sun and similar stars throughout the galaxy. 57. Planet formation began from dust. Planet formation began in the early solar system from tiny dust particles in a rotating disk of gas and debris around the Sun. These particles stuck together, forming larger clumps called planetesimals, which collided and merged over millions of years to create protoplanets. Gravity played a central role in drawing material together, forming the cores of rocky and gas giant planets. The process also created leftover material that became asteroids, comets, and moons. Understanding planet formation allows scientists to study the origin of Earth, other planets, and exoplanetary systems. Observations of protoplanetary disks around young stars today confirm that dust aggregation, accretion, and collisions are universal steps in forming planetary systems. The study of how dust evolved into fully formed planets provides insight into composition, planetary differentiation, and the potential for habitable worlds throughout the galaxy. This dust-to-planet process highlights the remarkable transformation from tiny particles to massive, complex planets over billions of years. 58. Mercury has an oversized core. Mercury has an unusually large metallic core that occupies about 85% of the planet's radius, much larger in proportion than any other rocky planet in the solar system. This massive core explains Mercury's high density, magnetic field, and geological activity despite its small size. Scientists believe Mercury's oversized core could result from an early giant impact that stripped away much of its original crust and mantle, or from processes that prevented silicate material from fully forming around the core. Mercury's core consists mainly of iron and nickel, surrounded by a thin silicate mantle and crust. The large core influences tectonics, magnetic field generation, and heat flow within the planet. Studying Mercury's core helps scientists understand planet formation, differentiation, and the effects of collisions and extreme solar proximity on small rocky worlds. Mercury's unique interior makes it a key laboratory for exploring the diversity of planetary structures in the inner solar system. 59. Venus has unbroken cloud layers. Venus is covered by thick, unbroken clouds of sulfuric acid that completely obscure its surface from view. These clouds reflect most sunlight, making Venus the brightest planet in the night sky, but they also trap heat through a runaway greenhouse effect, producing surface temperatures exceeding 460 degrees Celsius. The cloud layer is highly dynamic, with fast-moving winds circulating around the planet every 4 Earth days. The dense atmosphere prevents surface observations using visible light, so scientists rely on radar mapping and spacecraft flybys. Venus' continuous clouds play a critical role in atmospheric circulation, chemical reactions, and heat distribution. They are part of the reason Venus' climate is so extreme and serve as a natural laboratory for studying greenhouse effects and planetary atmospheres. Despite being similar in size to Earth, Venus' unbroken clouds and hostile surface environment make it one of the most enigmatic and extreme planets in the solar system. 60. Earth's oceans cover most surface. Earth's oceans cover about 71% of the planet's surface, playing a central role in regulating climate, weather, and supporting life. They store vast amounts of heat, drive ocean currents, and interact with the atmosphere to distribute energy and moisture around the globe. Oceans are home to immense biodiversity, from microscopic plankton to the largest whales, and provide essential resources for humans. They regulate carbon dioxide levels through biological and chemical processes, influencing global temperatures and climate stability. Earth's water cycle depends on oceans for evaporation, precipitation, and runoff, creating a continuous exchange of energy and matter. Studying oceans reveals patterns of climate change, marine ecosystems, and Earth's geologic history. Despite their size, oceans remain largely unexplored, with deep-sea regions holding unknown species and geological features. Covering most of the surface, oceans are essential for life, climate regulation, and the balance of the Earth system, making them one of the most important and dynamic components of our planet. 61. Mars' reddish color comes from rust. Mars' iconic reddish appearance comes from iron oxide, or rust, coating its surface rocks and soil. This iron-rich dust absorbs sunlight and reflects reddish wavelengths, giving the planet its red planet nickname. The rust forms over billions of years as iron in surface rocks oxidized in the presence of trace amounts of water and atmospheric oxygen. Mars' soil also contains a variety of other minerals, but the pervasive iron oxide dominates its color from space. Dust storms can lift this reddish dust high into the atmosphere, temporarily changing its appearance and reducing sunlight on the surface. The iron oxide also affects thermal properties, influencing how quickly the surface warms during the day and cools at night. Understanding Mars' reddish dust helps scientists learn about past water activity, chemical weathering, and the planet's climate history. Rovers and orbiters analyze surface samples to determine how iron and other elements reacted over time. Mars' rust-colored surface is not just visually striking but also a key to unraveling the planet's geological evolution and its potential to have once supported microbial life. 62. Jupiter protects Earth from comets. Jupiter, the largest planet in the solar system, acts as a cosmic shield for Earth by using its massive gravity to deflect or capture comets and asteroids that might otherwise collide with our planet. Its strong gravitational influence can pull objects from the outer solar system into new orbits, sometimes ejecting them entirely or sending them into the Sun. This protective role has reduced the frequency of catastrophic impacts on Earth, giving life a better chance to evolve over billions of years. Jupiter also shapes the structure of the asteroid belt and influences orbital dynamics across the solar system. However, its gravity can occasionally redirect objects toward the inner solar system, including Earth, creating potential impact risks. Understanding Jupiter's protective effects is crucial for studying planetary defense, asteroid trajectories, and the overall stability of our solar system. Observing how Jupiter interacts with comets, such as Shoemaker-Levy 9, provides direct evidence of its role in altering celestial paths and reducing threats to Earth while maintaining the delicate balance of planetary orbits across the solar system. 63. Saturn's rings may disappear someday. Saturn's stunning rings, composed of ice, dust, and rocky fragments, may not last forever. Scientists estimate that the rings are gradually losing material through a process called ring rain, where particles are pulled into Saturn's atmosphere by gravity and electromagnetic forces. Some rings may disappear entirely within tens to hundreds of millions of years. The ring's formation could be relatively recent in solar system terms, possibly resulting from a destroyed moon or leftover material that never formed a satellite. Their transient nature makes them a fleeting feature, spectacular for human observers but not permanent. Observing the rings allows scientists to study planetary formation, orbital dynamics, and interactions between dust, ice, and planetary magnetic fields. Understanding the rings' eventual disappearance helps explain why other giant planets, like Jupiter, have only faint rings and provides insight into the life cycle of planetary ring systems. Saturn's rings are a vivid reminder that even seemingly eternal celestial structures evolve and vanish over cosmic timescales, showing the dynamic nature of planetary systems. 64. Uranus winds reach incredible speeds. Uranus experiences some of the fastest winds among the giant planets, with speeds exceeding 900 km/h near its equator. These intense winds occur despite Uranus emitting very little internal heat compared to Neptune and other gas giants. The unusual axial tilt of approximately 98 degrees causes the planet to rotate almost on its side, creating extreme seasonal variations that influence atmospheric motion. Wind patterns are shaped by differential rotation, temperature contrasts, and interactions with the planet's thin cloud layers composed of methane and other gases. Storms and vortices, while less prominent than Neptune's, still occur and can last for extended periods. Observing Uranus winds helps scientists understand atmospheric dynamics on ice giants, the effects of extreme axial tilts, and the role of internal and external energy sources in driving planetary weather. The high-speed winds combined with frigid temperatures make Uranus an extreme and intriguing environment, revealing how atmospheric physics operates under conditions very different from those on Earth. Studying these winds enhances our understanding of both solar system planets and exoplanet atmospheres. 65. Neptune has faint ring arcs. Neptune's rings are faint and incomplete, forming distinct arcs rather than full circles around the planet. These arcs contain ice and dust particles trapped in narrow regions by gravitational interactions with Neptune's moons, particularly Galatea. Unlike Saturn's prominent rings, Neptune's are dark and difficult to observe in visible light, requiring specialized instruments and spacecraft imaging. The arcs appear to be relatively young and unstable, possibly reshaped over time by orbital resonances, collisions, and micrometeoroid impacts. Studying Neptune's ring arcs provides insight into how rings evolve, interact with moons, and persist despite being dynamically unstable. The faint arcs demonstrate the diversity of ring systems across the giant planets and highlight the complex gravitational interplay that maintains these structures. Observations from Voyager 2 and subsequent telescopes continue to reveal the arc's composition, size distribution, and temporal changes. Neptune's unusual ring arcs are an example of the delicate and transient nature of some celestial features in the outer solar system, emphasizing that even distant planets possess dynamic and evolving structures. 66. Pluto's surface shows active geology. Despite its distance from the Sun, Pluto displays evidence of active geology, with plains, mountains, glacier, and possible cryovolcanoes reshaping its surface. New Horizons flyby revealed nitrogen ice plains like Sputnik Planitia, which appear young and relatively free of impact craters, suggesting ongoing resurfacing. Tectonic features indicate that Pluto's interior may have retained heat, allowing ice to flow and deform. Seasonal sublimation and condensation of nitrogen and methane ice create dynamic surface changes over its orbit. Pluto's diverse surface terrain, including mountain ranges and pits, challenges the perception of it as a static, frozen dwarf planet. Studying Pluto's geology provides insight into cryovolcanism, ice dynamics, and the long-term evolution of Kuiper Belt objects. Active processes on Pluto suggest that even small, distant worlds can exhibit complex geological activity driven by internal heat, ice movement, and interactions with the Sun's energy. Pluto's geology makes it a valuable target for understanding the diversity of planetary surfaces beyond the main planets. 67. Solar system is mostly empty. Although filled with planets, moons, asteroids, and comets, the solar system is mostly empty space. Vast distances separate celestial bodies, with millions of kilometers between planets and even greater stretches to the outer regions like the Kuiper Belt and Oort Cloud. Space is a near-perfect vacuum, containing extremely sparse gas, dust, and cosmic rays. This emptiness allows planets to orbit the Sun with minimal interference and provides a stable environment for long-term orbital dynamics. While objects may occasionally collide or pass near each other, the vast emptiness makes such events rare. Understanding the distribution of matter and voids in the solar system helps astronomers calculate gravitational interactions, plan spacecraft missions, and predict trajectories of comets and asteroids. This emptiness is also essential for observing the universe beyond, as light and signals travel unimpeded. The largely empty nature of the solar system highlights both its scale and the relative isolation of planets and other objects, demonstrating how sparse matter can still form complex, dynamic systems across billions of kilometers. 68. The Sun will eventually expand. The Sun, a middle-aged star, will eventually exhaust its hydrogen fuel in the core, causing it to expand into a red giant billions of years from now. During this phase, the Sun's outer layers will swell, potentially engulfing the inner planets, including Mercury and Venus, and dramatically increasing the heat and radiation reaching Earth. The core will contract and heat up, eventually fusing helium into heavier elements. This expansion is part of the natural life cycle of medium-sized stars like the Sun. Following the red giant stage, the Sun will shed its outer layers to form a planetary nebula, leaving behind a dense white dwarf. Understanding this process helps scientists predict the future evolution of our solar system and the ultimate fate of Earth and neighboring planets. Observing other stars in various stages of life provides models for how the Sun's expansion will occur. While billions of years away, this inevitable expansion shapes long-term perspectives on planetary habitability, star life cycles, and cosmic evolution. 69. Mercury has ice in craters. Despite being the closest planet to the Sun, Mercury has pockets of water ice hidden in permanently shadowed craters at its poles. These craters never receive sunlight, allowing temperatures to remain low enough for ice to persist for billions of years. Radar observations from Earth and spacecraft like Messenger confirmed the presence of ice, sometimes covered by a thin layer of dark material that insulates it. Mercury's ice likely arrived via cometary impacts or was preserved from the early solar system. Studying these ice deposits provides clues about volatile retention on small, hot worlds and the history of water in the inner solar system. Ice on Mercury also offers insight into the planet's geology, impact cratering, and thermal environment. These shadowed craters demonstrate that even extreme environments can preserve essential compounds like water, expanding our understanding of where ice can exist beyond Earth. 70. Venus has the longest rotation. Venus has the slowest rotation of any planet in the solar system, taking about 243 Earth days to complete one rotation, longer than its year of 225 Earth days. Interestingly, it rotates retrograde, spinning opposite to its orbital motion, so the Sun rises in the west and sets in the east. This extremely slow rotation contributes to uniform surface temperatures, extreme greenhouse conditions, and a thick, turbulent atmosphere of carbon dioxide with sulfuric acid clouds. The slow spin affects wind patterns, heat distribution, and weather systems, creating superrotating winds that circle the planet much faster than its rotation. Venus' unusual rotation is thought to result from a giant impact or tidal interactions early in its history. Studying Venus' slow rotation helps scientists understand planetary dynamics, atmospheric behavior, and why two similar-sized planets, Earth and Venus, evolved so differently. Venus' long day demonstrates how rotation influences climate, habitability, and atmospheric processes on terrestrial planets. 71. Earth's axis slowly wobbles. Earth's axis experiences a slow wobble, known as axial precession, which completes a cycle approximately every 26,000 years. This gradual change in orientation affects the positions of the stars, alters the timing of seasons, and influences long-term climate patterns, including ice ages. Precession occurs because gravitational forces from the Sun and Moon tug on Earth's equatorial bulge, causing it to slowly rotate like a spinning top. This wobble also shifts the locations of celestial poles and the timing of equinoxes, which can slightly alter solar insolation over millennia. Understanding axial precession is crucial for studying Earth's climate history, modeling future seasonal changes, and interpreting ancient astronomical records. Precession interacts with other orbital variations, such as eccentricity and obliquity, in a combination known as Milankovitch cycles, which strongly influence Earth's long-term climate cycles. Monitoring this slow wobble helps scientists understand the delicate balance of forces affecting our planet's rotation and contributes to accurate astronomical predictions and navigation. Earth's axial wobble demonstrates the dynamic and interconnected nature of planetary motion within the solar system. 72. Mars has deep canyons. Mars is home to Valles Marineris, one of the deepest and longest canyon systems in the solar system, stretching over 4,000 kilometers and reaching depths of up to 7 kilometers. These canyons dwarf Earth's Grand Canyon in both size and scale, offering insight into tectonic, erosional, and volcanic processes on the Red Planet. Scientists believe the canyons formed primarily through tectonic stretching, crustal cracking, and possibly ancient water flow, which carved out channels and contributed to layered sedimentary deposits. Studying these features helps researchers understand Mars' geological history, including crustal stress, volcanic activity, and potential past water presence. The canyons may also preserve clues about past climates and environmental conditions that could have supported microbial life. Robotic missions and orbiters use high-resolution imaging to map and analyze the complex canyon terrain, revealing cliffs, landslides, and faults. Valles Marineris demonstrates that even a planet without plate tectonics like Earth can develop immense and geologically complex structures, providing a window into Mars' dynamic past and ongoing surface evolution. 73. Jupiter has metallic hydrogen inside. Deep within Jupiter, extreme pressures compress hydrogen into a metallic form, creating a layer that conducts electricity and contributes to the planet's immense magnetic field. This metallic hydrogen exists under pressures exceeding millions of atmospheres and temperatures of tens of thousands of degrees, making it one of the most exotic states of matter in the solar system. The metallic layer lies above Jupiter's dense core and interacts with surrounding molecular hydrogen to generate convection currents, producing strong magnetic activity, auroras, and radiation belts. Studying metallic hydrogen provides insight into the internal structure, rotation, and heat transport of gas giants, which cannot be directly observed. Laboratory experiments on Earth attempt to recreate metallic hydrogen conditions, offering clues about superconductivity and extreme physics. Jupiter's magnetic field, powered by metallic hydrogen, protects its moons and shapes the space environment around the planet. Understanding this unusual hydrogen state helps scientists model the interiors of exoplanets, providing analogues for other massive gas giants across the galaxy. Metallic hydrogen is a key factor in explaining Jupiter's magnetic intensity, deep atmospheric behavior, and the planet's overall structure. 74. Saturn's moon Enceladus ejects water. Enceladus, one of Saturn's icy moons, continuously ejects water vapor, ice particles, and organic compounds from cracks near its south pole. These geysers, called tiger stripes, indicate a subsurface ocean beneath the moon's frozen crust, kept liquid by tidal heating from Saturn's gravity. The ejected material contributes to Saturn's earring and may contain the chemical ingredients necessary for life. Observations by the Cassini spacecraft detected salt, organic molecules, and complex chemistry in the plumes, suggesting an environment that could support microbial life. Enceladus active geology challenges previous assumptions about small icy moons being inactive and frozen. Studying these plumes helps scientists understand cryovolcanism, internal heating, and the potential habitability of icy worlds in the outer solar system. Future missions may sample these ejected materials directly to search for signs of life, making Enceladus one of the most promising locations beyond Earth for astrobiological research. Its continuous water ejection makes it a natural laboratory for understanding planetary processes and the dynamics of subsurface oceans. 75. Uranus rains solid diamonds. Deep inside Uranus, extreme pressures and temperatures may compress carbon into solid diamond, forming diamond rain. Methane in the planet's interior breaks down, releasing carbon atoms that crystallize and fall toward the core. This exotic form of precipitation contributes to Uranus' internal heat and provides insight into the behavior of materials under extreme conditions. Diamond rain has been hypothesized for both Uranus and Neptune, making them unique laboratories for studying high-pressure physics and chemical reactions not possible on Earth. Understanding this process helps scientists model ice giant interiors, their heat transport, and magnetic fields. Although direct observation is impossible with current technology, theoretical models and laboratory simulations support the possibility of diamond formation. Uranus diamond rain highlights the diversity of physical phenomena in the solar system and the extraordinary conditions that exist on planets unlike Earth. It reveals how extreme environments can produce phenomena that challenge our everyday understanding of physics and chemistry. 76. Neptune formed far from Sun. Neptune, the outermost giant planet, formed in the cold reaches of the solar system, far from the Sun. Its formation likely involved accumulation of ices, hydrogen, helium, and rocky material over tens of millions of years, influenced by the gravitational effects of Jupiter and Saturn. Being distant from the Sun, Neptune's growth was slower than that of inner planets, and its core may have captured a thick gaseous envelope, forming the ice giant we see today. Its position also influenced the capture and arrangement of moons, rings, and surrounding Kuiper Belt objects. Neptune's early formation far from the Sun helps explain its composition, atmosphere, and strong internal heat despite minimal solar input. Studying Neptune's formation sheds light on ice giant formation, orbital migration, and the evolution of planetary systems, both in our solar system and around other stars. Its distant origin contributes to its cold temperature, vivid blue color from methane absorption, and unique orbital interactions. 77. Pluto's orbit is highly elliptical. Pluto follows a highly elliptical orbit around the Sun, ranging from about 30 to 49 astronomical units. This extreme eccentricity causes significant variations in solar energy reaching the dwarf planet, influencing atmospheric density and seasonal changes. During perihelion, when Pluto is closest to the Sun, some of its frozen nitrogen, methane, and carbon monoxide sublimates into a temporary atmosphere, while during aphelion, gases freeze back onto the surface. Its orbit is also inclined relative to the planets, creating a path that sometimes crosses Neptune's orbit without collision due to orbital resonance. Studying Pluto's elliptical orbit provides insight into the dynamics of the Kuiper Belt, gravitational interactions, and the behavior of small, distant objects in the solar system. The orbit also helps explain geological activity, seasonal surface changes, and atmospheric phenomena observed by New Horizons. Pluto's path demonstrates that even small bodies can follow complex, highly elongated trajectories shaped by gravitational forces over billions of years. 78. Solar system lies in Orion Arm. Our solar system resides within the Orion Arm, a minor spiral arm of the Milky Way galaxy located between the larger Perseus and Sagittarius arms. Positioned about 27,000 light-years from the galactic center, the Orion Arm provides a relatively stable environment with sufficient distance from the high-density regions of the galactic core, reducing exposure to supernovae and gravitational disturbances. This location has influenced the formation and long-term stability of the solar system and contributed to Earth's habitability. Observations of nearby stars, nebulae, and star-forming regions help map the structure of the Orion Arm and understand the distribution of matter in the Milky Way. Studying the solar system's position in the galaxy allows astronomers to contextualize cosmic evolution, stellar populations, and the potential for life elsewhere. Being in the Orion Arm also gives astronomers an ideal vantage point for observing other parts of the galaxy. The solar system's location highlights the interplay between galactic structure and the conditions necessary for planetary formation and life. 79. The Sun orbits the galaxy. The Sun, along with the entire solar system, orbits the center of the Milky Way galaxy at an average speed of about 828,000 kilometers per hour, completing one orbit approximately every 225 to 250 million years. This galactic orbit keeps the solar system within the relatively calm Orion Arm, avoiding the dense core where conditions could threaten planetary stability. The Sun's motion is influenced by gravitational forces from the galactic center, neighboring stars, and dark matter. Its orbit also causes vertical oscillations above and below the galactic plane, impacting cosmic ray exposure over geological timescales. Understanding the Sun's motion helps astronomers model the dynamics of the Milky Way, the distribution of stars and interstellar material, and the solar system's exposure to astrophysical events. The orbit also provides context for long-term climate variations and mass extinction patterns on Earth linked to galactic position. The Sun's path through the galaxy is a key factor shaping the environment in which our solar system evolves. 80. Mercury's orbit precession puzzled scientists. Mercury's orbit slowly precesses, meaning its elliptical path rotates over time, a phenomenon that puzzled scientists for centuries because Newtonian mechanics could not fully account for the observed rate. The precession is caused by the gravitational influence of other planets and subtle effects from general relativity, as confirmed by Einstein's theory in the early 20th century. Mercury's orbit shifts slightly with each revolution, affecting its perihelion, the closest point to the Sun, and producing measurable changes over decades. Understanding this precession was a major breakthrough in physics, providing one of the first confirmations of general relativity. Studying Mercury's orbital behavior also informs models of planetary dynamics, gravitational interactions, and celestial mechanics. Observations of Mercury continue to refine our understanding of solar system mechanics, the Sun's mass distribution, and relativistic effects. Mercury's orbital precession exemplifies the subtle but important influences that govern planetary motion and the power of modern physics to explain phenomena once thought mysterious. 81. Venus clouds reflect intense sunlight. Venus is covered by thick clouds composed mainly of sulfuric acid droplets, which reflect a large portion of incoming sunlight, giving the planet its bright, reflective appearance in the sky. These clouds create a high albedo, meaning Venus appears very bright from Earth, second only to the Moon in visibility. The dense cloud layer traps heat in a runaway greenhouse effect, raising surface temperatures to around 465 degrees Celsius, hotter than Mercury despite being farther from the Sun. These reflective clouds also obscure the planet's surface in visible light, requiring radar mapping to study its terrain. Understanding Venus clouds helps scientists explore atmospheric chemistry, climate dynamics, and planetary greenhouse effects. Observations of cloud motion reveal high-speed winds circulating around the planet, reaching hundreds of kilometers per hour in the upper atmosphere. Venus clouds demonstrate how a planet's atmosphere can dominate its appearance, influence climate, and create extreme environmental conditions unlike any other planet in the solar system. Studying them provides insight into both exoplanet atmospheres and the evolution of terrestrial planets. 82. Earth's continents constantly drift. Earth's continents are not fixed, they slowly drift across the planet's surface due to plate tectonics. The lithosphere is broken into large plates that float atop the semifluid asthenosphere, moving at rates of a few centimeters per year. This motion causes earthquakes, volcanic activity, mountain formation, and the creation of ocean basins. Continents have collided and separated over billions of years, forming supercontinents like Pangaea and then drifting apart to their present positions. Plate tectonics also plays a crucial role in the carbon cycle, climate regulation, and the evolution of life by reshaping habitats. Studying continental drift helps geologists understand Earth's geological history, predict natural disasters, and locate mineral resources. Modern GPS technology measures plate movements with incredible precision, confirming the dynamic nature of Earth's crust. Continental drift explains the distribution of fossils, similar rock formations across continents, and patterns in mountain ranges and ocean trenches. This constant motion demonstrates that Earth is a living, evolving planet, where the surface changes continuously on geological timescales. 83. Mars might hold ancient microbes. Mars, the red planet, may have hosted microbial life in its distant past. Evidence of ancient water flows, riverbeds, and mineral deposits suggests that liquid water once existed on its surface, creating potentially habitable environments. Rovers and orbiters have detected organic molecules, seasonal methane variations, and chemical signatures indicating past or present microbial activity. Scientists study these signs to understand the planet's climate history, geochemical cycles, and potential for life beyond Earth. Even though the surface is now cold, dry, and exposed to radiation, underground aquifers or transient water activity might still support microbial life. Finding evidence of past life on Mars would revolutionize our understanding of biology and the distribution of life in the solar system. Ongoing missions, such as the Perseverance rover and future sample return projects, aim to confirm whether microbes once existed on Mars. This exploration informs planetary protection strategies, guides the search for life on exoplanets, and helps determine the conditions necessary for life in extreme environments. 84. Jupiter's auroras are enormous. Jupiter hosts the largest and most powerful auroras in the solar system, hundreds of times stronger than those on Earth. Caused by charged particles from the solar wind and volcanic material from its moon Io, these particles spiral along Jupiter's magnetic field lines and collide with the upper atmosphere, emitting brilliant light. Jupiter's auroras are visible in ultraviolet and infrared wavelengths and can cover regions larger than Earth itself. The planet's strong magnetic field and rapid rotation enhance auroral intensity and structure, creating complex, dynamic displays. Studying Jupiter's auroras helps scientists understand magnetospheric physics, particle acceleration, and the interactions between a planet and its moons. Spacecraft like Hubble and Juno provide detailed observations of auroral patterns, revealing variations over time and links to internal and external influences. Jupiter's immense auroras demonstrate the extreme electromagnetic environment of gas giants, highlighting differences in planetary magnetic activity compared to Earth. Observing these spectacular phenomena improves understanding of planetary magnetospheres, auroral mechanics, and the effects of solar wind throughout the solar system. 85. Saturn's hexagon storm is persistent. Saturn's North Pole hosts a massive, long-lived storm shaped like a hexagon, roughly 30,000 kilometers across. First observed by Voyager and later studied by Cassini, the hexagon is a jet stream with winds rotating at about 320 kilometers per hour. Its unique geometric shape is created by the combination of differential rotation, atmospheric waves, and fluid dynamics under extreme planetary conditions. The storm persists for decades or longer, indicating stable atmospheric patterns in Saturn's polar region. Studying the hexagon provides insight into planetary meteorology, fluid behavior on a large scale, and the physics of long-lasting storms in gas giants. Unlike Earth's cyclones, Saturn's hexagon has no clear center and remains fixed relative to the planet's rotation. Observations of the storm in visible, infrared, and ultraviolet light reveal seasonal changes, chemical compositions, and interactions with surrounding clouds. Saturn's hexagon demonstrates how complex and stable atmospheric patterns can emerge naturally on other planets, offering a unique window into the behavior of giant planet atmospheres. 86. Uranus experiences extreme seasons. Uranus' unusual axial tilt of approximately 98 degrees causes extreme seasonal variations, with each pole experiencing 42 years of continuous sunlight followed by 42 years of darkness. This sideways rotation creates dramatic differences in temperature, atmospheric circulation, and wind patterns throughout its long orbit. Uranus' upper atmosphere shows faint cloud bands and storms influenced by these extreme seasonal cycles, which differ from the more uniform patterns seen on other planets. The tilt may have resulted from a massive collision early in the planet's history, drastically affecting its evolution and internal dynamics. Seasonal variations also influence the visibility of cloud features and the distribution of methane in the atmosphere. Studying Uranus seasons provides insight into planetary tilts, atmospheric behavior, and how extreme obliquity shapes climate and weather patterns. These extreme seasonal changes make Uranus a unique laboratory for understanding ice giant atmospheres, energy balance, and the effects of axial tilt on planetary environments. 87. Neptune has active dynamic weather. Neptune experiences some of the most active and dynamic weather in the solar system. Its atmosphere exhibits fast winds, reaching over 2,000 kilometers per hour, the fastest recorded on any planet. Giant storms, vortices, and cloud formations appear and dissipate rapidly, driven by internal heat escaping from the planet's interior. Despite being far from the Sun, Neptune radiates more energy than it receives, powering this intense weather system. Observations from Voyager 2 and Earth-based telescopes reveal changing storm patterns, transient dark spots, and bright methane clouds. Studying Neptune's dynamic weather helps scientists understand atmospheric physics under extreme conditions, the behavior of ice giants, and comparative meteorology across planets. The planet's storms demonstrate that weather activity does not solely depend on solar input but can be sustained by internal energy and complex atmospheric interactions. Neptune's extreme weather provides a valuable contrast to slower-moving atmospheres like Uranus or Venus. 88. Pluto may have underground oceans. Evidence from surface features, such as tectonic cracks, ice plains, and depressions, suggests that Pluto may harbor a subsurface ocean beneath its icy crust. This ocean could be kept liquid by residual heat from radioactive decay and antifreeze compounds like ammonia. The potential presence of liquid water makes Pluto a candidate for astrobiological studies, as subsurface oceans provide environments where microbial life could exist. Cryovolcanic activity and surface deformations hint at interactions between the ocean and the icy shell, shaping Pluto's landscape over billions of years. Understanding underground oceans on Pluto helps scientists explore the habitability of distant icy worlds and the potential for life beyond Earth. Observations from the New Horizons mission continue to inform models of interior composition, thermal evolution, and surface dynamics. Pluto's hidden ocean demonstrates that even small, cold celestial bodies can retain complex and active internal systems. 89. Solar wind flows continuously outward. The Sun constantly emits a stream of charged particles called a solar wind, which flows outward through the solar system at speeds of hundreds of kilometers per second. This wind shapes planetary magnetospheres, forms the heliosphere, and interacts with comets, causing their tails to point away from the Sun. Solar wind particles can trigger auroras on planets with magnetic fields and occasionally disrupt satellites, power grids, and communication systems on Earth. The solar wind varies with solar activity, increasing during flares and coronal mass ejections. Understanding its behavior is essential for space weather forecasting, planetary science, and protecting spacecraft and astronauts. The solar wind also helps sculpt the edges of the solar system, influencing the termination shock and heliopause, where it meets interstellar space. Its continuous outward flow demonstrates the Sun's influence far beyond its visible light and highlights the interconnected nature of the Sun and its planetary system. 90. Sunspots affect solar output. Sunspots are dark, cooler regions on the Sun's surface caused by intense magnetic activity that inhibits convection. While cooler than surrounding areas, sunspots are often associated with solar flares and increased solar radiation. The number and frequency of sunspots follow an approximately 11-year cycle, influencing the Sun's overall luminosity and magnetic activity. Variations in solar output caused by sunspots can affect Earth's climate, satellite operations, and radio communications. Large sunspots can produce coronal mass ejections that interact with planetary magnetic fields, creating spectacular auroras but also posing hazards to technology. Studying sunspots helps astronomers understand the Sun's magnetic dynamo, internal processes, and long-term behavior. Observations of sunspots over centuries provide valuable data for predicting solar cycles and modeling solar-terrestrial interactions. Sunspots demonstrate that even small surface features on the Sun can have significant effects throughout the solar system, highlighting the dynamic nature of our star. 91. Mercury has a magnetosphere. Mercury, despite being small and close to the Sun, possesses a magnetic field, or magnetosphere, that protects part of its surface from solar wind. This magnetosphere is about 1% the strength of Earth's, but is still significant in deflecting charged particles. Generated by a partially molten, iron-rich core, it reveals that Mercury retains internal heat and a dynamic interior despite its size and age. The magnetosphere interacts with the solar wind to create auroras near the poles and influences the motion of charged particles around the planet. Studying Mercury's magnetosphere helps scientists understand planetary dynamos, magnetic field evolution, and how small planets can maintain magnetic protection over billions of years. Observations from MESSENGER revealed its structure, strength, and peculiarities, such as asymmetry caused by solar wind pressure. Mercury's magnetosphere also contributes to space weathering on the surface, shaping its thin exosphere and affecting volatile retention. By understanding Mercury's magnetic environment, researchers gain insight into the history of the planet's interior, its geological evolution, and how magnetospheres operate under extreme proximity to the Sunday 92. Venus has sulfuric acid clouds. Venus' atmosphere is covered by dense clouds composed mainly of sulfuric acid droplets, creating a highly reflective layer that obscures the surface from visible light. These clouds contribute to a runaway greenhouse effect, trapping heat and raising surface temperatures above 460 degrees Celsius, hotter than Mercury. The clouds move in superrotating winds, circling the planet much faster than its rotation, and create constant storms and turbulence in the upper atmosphere. Studying these clouds provides insight into atmospheric chemistry, cloud formation, and extreme climate conditions. Sulfuric acid clouds interact with sunlight, scattering light and producing Venus-bright appearance in the night sky. Understanding these clouds is also important for modeling exoplanetary atmospheres, as similar thick acidic clouds may exist on distant worlds. Their dynamic behavior, chemical composition, and interaction with surface heat reveal the mechanisms behind greenhouse warming and extreme weather patterns. Venus clouds illustrate how planetary atmospheres can create harsh, uninhabitable conditions while shaping the planet's visual characteristics and climate system over billions of years. 93. Earth hosts a breathable atmosphere. Earth's atmosphere is unique in the solar system, composed of roughly 78% nitrogen, 21% oxygen, and trace gases, providing breathable air for life. Oxygen is produced primarily by photosynthetic organisms, including plants, algae, and cyanobacteria, which have maintained a stable concentration for hundreds of millions of years. The atmosphere protects life from harmful solar radiation, regulates temperature, and allows water to remain liquid on the surface. Layers like the stratosphere contain ozone, which absorbs ultraviolet light, preventing widespread biological damage. Earth's atmosphere also drives weather patterns, distributes heat, and supports the water cycle, creating climates suitable for diverse ecosystems. Understanding the formation, evolution, and composition of Earth's atmosphere helps scientists study habitability, climate change, and the search for life on exoplanets. Comparisons with Venus, Mars, and other planets show how atmospheric composition directly impacts temperature, surface conditions, and the potential for sustaining life. Earth's breathable atmosphere is a rare and vital feature, sustaining complex life forms while interacting with oceans, land, and biological processes over geological timescales. 94. Mars has a thin atmosphere. Mars' atmosphere is extremely thin, composed mostly of carbon dioxide, with traces of nitrogen and argon, creating pressures less than 1% of Earth's. This thin layer cannot retain heat effectively, contributing to frigid temperatures and extreme daily fluctuations. Dust storms can envelop the entire planet, and the lack of substantial atmospheric pressure prevents liquid water from persisting on the surface. Despite its thinness, the atmosphere plays a role in shaping surface features through wind erosion and dust transport. Seasonal variations influence polar ice caps and release small amounts of carbon dioxide gas. Studying Mars' thin atmosphere helps scientists understand planetary climate evolution, volatile loss, and the potential for future human exploration. Observations from orbiters and rovers reveal interactions between the atmosphere, surface, and subsurface ice. Mars' tenuous atmosphere contrasts sharply with Earth's thick, life-supporting air and demonstrates how planetary size, gravity, and proximity to the Sun influence atmospheric retention. Understanding these conditions is essential for exploring habitability and designing technology for manned missions. 95. Jupiter's gravity shapes asteroid belt. Jupiter's immense gravity influences the asteroid belt located between Mars and Jupiter, creating gaps known as Kirkwood gaps where orbital resonances prevent stable asteroid paths. Its gravitational pull helps maintain the belt structure, prevents planet formation in this region, and occasionally redirects asteroids toward the inner solar system. Jupiter also protects Earth by capturing or deflecting comets and other potentially hazardous objects. Studying its gravitational influence provides insight into planetary formation, orbital dynamics, and the early evolution of the solar system. The planet's massive mass disturbs smaller bodies, creating collisions, fragmenting asteroids, and contributing to meteor populations. Observations of asteroid orbits, belt distribution, and collisions allow scientists to understand Jupiter's role in shaping the solar system's architecture. Jupiter's gravity demonstrates how giant planets can stabilize or destabilize surrounding material, influencing planetary habitability and the formation of terrestrial worlds. This gravitational dominance is a key factor in the long-term evolution and safety of the inner solar system. 96. Saturn's moons influence ring structure. Saturn's diverse moons play a significant role in shaping the structure and stability of its rings. Small moons called shepherd satellites confine ring particles through gravitational interactions, maintaining sharp edges and gaps. Moons like Mimas and Pan create resonances that form features such as the Cassini division. Larger moons also contribute material to the rings through impact ejecta, replenishing dust and ice particles. Observing these interactions reveals the delicate balance of forces within the ring system, including collisions, resonances, and orbital perturbations. Studying Saturn's moons and rings helps scientists understand planetary formation, satellite dynamics, and the evolution of ring systems around giant planets. Rings are not static. They continuously change due to the gravitational influences of nearby moons. These dynamic relationships provide a laboratory for understanding the behavior of particulate matter in orbit, offering insights applicable to exoplanetary ring systems and disk formation in young stellar systems. 97. Uranus has mysterious internal chemistry. Uranus' interior contains a mixture of water, ammonia, methane, and other ices, forming a fluid layer that generates its magnetic field in unusual patterns. Scientists know little about the exact chemical composition and interactions within its mantle due to limited observations. The planet emits less heat than expected, suggesting unusual internal processes or layered convection. Methane in the atmosphere absorbs red light, giving Uranus its blue-green color. Studying Uranus chemistry helps researchers model ice giant formation, magnetic fields, and heat transport mechanisms. Laboratory experiments simulate extreme pressures and temperatures to understand how materials behave inside ice giants. Uranus' unique tilt also influences chemical distribution and circulation in the interior. Understanding its internal chemistry provides insight into the diversity of planetary structures, the evolution of the outer solar system, and the potential compositions of exoplanets with similar characteristics. 98. Neptune's atmosphere contains methane. Neptune's vivid blue color comes from methane gas in its upper atmosphere, which absorbs red light and reflects blue. The atmosphere consists of hydrogen, helium, and methane, with dynamic cloud systems and high-speed winds. Methane clouds form bright bands and storms, while deeper layers may contain other ices and chemicals. Methane influences thermal properties, infrared emission, and energy transport within the atmosphere. Studying Neptune's methane-rich environment helps scientists understand ice giant atmospheres, atmospheric chemistry, and the effects of solar and internal energy on weather systems. Observations from Voyager 2 and Earth-based telescopes reveal variations in cloud patterns, seasonal changes, and storm evolution. Methane on Neptune provides a key comparison point for understanding Uranus, exoplanets, and the chemical diversity possible in outer planetary atmospheres. 99. Pluto's glacier slowly shift. Pluto's surface contains glacier composed of nitrogen, methane, and carbon monoxide ice that move gradually due to internal heat and surface sublimation. These glacier reshape the landscape, filling basins, creating smooth plains, and interacting with surrounding mountains. Flow patterns and fractures suggest a convecting ice layer, providing evidence of ongoing geological activity despite Pluto's small size and distant, cold environment. Studying these shifting glacier helps scientists understand cryovolcanism, surface-atmosphere interactions, and the long-term evolution of distant icy worlds. Observations from New Horizons reveal flowing nitrogen ice and glacial deposits reshaping valleys and plains, demonstrating that Pluto is not a static, frozen world. Glacial movement also affects surface coloration, textures, and possible subsurface water pockets, making Pluto a dynamic example of planetary processes far from the Sunday 100. Solar system formed from nebula. The solar system originated about 4.6 billion years ago from a giant rotating cloud of gas and dust called the solar nebula. Gravity caused the nebula to collapse, forming the Sun at its center while the remaining material flattened into a protoplanetary disk. Planetesimals coalesced into planets, moons, asteroids, and comets through accretion and collisions. The composition of each planet depended on its distance from the Sun, with rocky planets forming close in and gas giants forming farther out. Studying solar nebula models helps scientists understand planetary formation, chemical differentiation, and the distribution of water and organic materials. Isotopic analysis of meteorites provides evidence of early solar system processes, including the timing of formation, temperature gradients, and mixing of materials. The nebula origin explains the organized orbital motions, compositional variations, and the presence of leftover debris like the asteroid and Kuiper belts. Understanding this process provides insight into how other star systems and planets form throughout the galaxy. 101. The Sun accounts for 99.8%. The Sun contains 99.8% of the total mass of the solar system, dominating gravitational forces and controlling the motion of all planets, comets, and asteroids. Its immense mass creates a powerful gravitational pull that maintains orbital stability and drives planetary dynamics. The Sun's mass also determines the location of the barycenter, the center of mass around which planets orbit, and affects orbital resonances and stability. Energy from the Sun fuels Earth's climate, photosynthesis, and weather systems. Studying the Sun's mass and structure provides insight into stellar physics, solar evolution, and the life cycles of stars similar to it. Despite containing nearly all the system's mass, the Sun occupies a tiny fraction of the volume compared to the distances between planets, highlighting the emptiness of interplanetary space. Understanding the Sun's dominance explains why the solar system remains stable over billions of years and why planets and smaller bodies follow predictable orbits. 102. Mercury's night side reaches extreme cold. Mercury experiences extreme temperature variations between day and night due to its lack of a significant atmosphere. While daytime temperatures exceed 430 degrees Celsius, the night side can plummet to -180 degrees Celsius. This extreme cold occurs because there is no atmospheric blanket to retain heat after the sun sets. Temperature fluctuations affect surface geology, causing thermal stress, cracking, and regolith formation. Polar craters in permanent shadow can harbor water ice, preserved by the frigid nightside conditions. Understanding Mercury's thermal environment helps scientists model exoplanets with thin or no atmospheres and study planetary heat retention mechanisms. Spacecraft measurements reveal how sunlight absorption and reflection, thermal inertia, and surface composition influence temperature extremes. These extremes also affect the stability of volatiles, magnetic interactions, and potential resource availability for future exploration. Mercury's night side illustrates how proximity to the Sun, lack of atmosphere, and small size combine to create dramatic environmental contrasts. 103. Venus atmosphere spins super fast. Venus atmosphere rotates around the planet approximately 60 times faster than the planet itself, a phenomenon called superrotation. High-altitude winds move at speeds up to 360 kilometers per hour, circulating clouds around the globe in just 4 Earth days. This extreme motion contrasts with Venus' slow retrograde rotation, creating complex atmospheric dynamics. Superrotation drives weather patterns, heat distribution, and the formation of dense cloud layers composed of sulfuric acid. The mechanism behind this phenomenon is still under study, with factors like thermal tides, solar heating, and surface-atmosphere interactions contributing. Understanding superrotation informs scientists about atmospheric behavior under extreme conditions, applicable to exoplanets and theoretical climate models. Venus' fast-spinning atmosphere demonstrates that atmospheric dynamics can differ greatly from planetary rotation, creating exotic weather systems and shaping the planet's persistent greenhouse conditions. Studying this behavior helps explain how energy, momentum, and chemical processes interact on a terrestrial planet with a dense, toxic atmosphere. 104. Earth's oxygen came from microbes. Earth's breathable oxygen was produced primarily by microscopic organisms called cyanobacteria through photosynthesis over billions of years. Early in Earth's history, the atmosphere had little free oxygen, but the Great Oxidation Event around 2.4 billion years ago increased oxygen levels dramatically. This process allowed aerobic life to evolve and led to the formation of the ozone layer, which shields the surface from harmful ultraviolet radiation. Oxygen production continues today via plants, algae, and other photosynthetic organisms. Understanding the microbial origin of oxygen helps scientists study Earth's climate history, evolution of life, and biosignatures for detecting life on exoplanets. The presence of oxygen demonstrates the profound impact of microbial activity on planetary conditions, altering chemistry, climate, and habitability. Earth's oxygenation exemplifies how life can transform a planet's atmosphere and create conditions suitable for complex ecosystems. 105. Mars has seasons like Earth. Mars experiences seasons similar to Earth due to its axial tilt of 25 degrees, slightly greater than Earth's 23.5 degrees. These seasons cause variations in temperature, atmospheric pressure, and polar ice cap size throughout its 687-day orbit. Spring and summer in each hemisphere lead to sublimation of carbon dioxide ice, while autumn and winter see deposition and expansion of ice caps. Seasonal changes also drive dust storms, frost formation, and weather patterns affecting surface features. Observing Martian seasons helps scientists understand climate cycles, atmospheric dynamics, and potential habitability. Seasonal shifts influence surface geology, including the formation of gullies, landslides, and frost-related features. Studying Mars' seasonal behavior provides analogues for understanding climate evolution on Earth and other terrestrial planets. These seasonal cycles demonstrate that even a thin atmosphere and cold temperatures can produce complex, cyclical environmental changes over time. 106. Jupiter's moons form a mini-system. Jupiter's numerous moons create a complex minisystem around the gas giant, with the four largest, Io, Europa, Ganymede, and Callisto, known as the Galilean moons. Each has unique geological features, atmospheres, and potential subsurface oceans, forming a system almost like a miniature planetary neighborhood. Their gravitational interactions produce tidal forces that influence volcanic activity, internal heating, and orbital resonance patterns. Io's volcanoes erupt constantly due to tidal heating, Europa may harbor a subsurface ocean, and Ganymede has its own magnetic field. Studying these moons provides insight into satellite formation, planetary dynamics, and the potential for life in diverse environments. The moon's interactions with Jupiter's powerful magnetosphere also create radiation belts and auroral phenomena, shaping both surface and atmospheric conditions. Observing Jupiter's minisystem helps scientists understand how complex gravitational relationships shape planetary systems and how moons can develop varied geological and chemical environments. This minisystem offers a natural laboratory for studying the evolution of moons, tidal heating, and conditions necessary for potential habitability beyond Earth. 107. Saturn's rings may be young. Saturn's iconic rings may be much younger than the planet itself, possibly forming only a few 100 million years ago. Composed primarily of ice particles with traces of rock, the rings appear bright and clean, suggesting they have not been heavily darkened by cosmic dust. The origin of the rings may involve the destruction of a moon or comet that broke apart under Saturn's gravity. Observations from Cassini reveal complex structures, gaps, and waves caused by gravitational interactions with Saturn's moons. Studying the rings' composition and age helps scientists understand planetary ring dynamics, satellite interactions, and the processes that shape debris disks around other planets and stars. The rings constantly evolve as particles collide, clump, and drift, providing insight into orbital mechanics, particle behavior, and resonance effects. Understanding Saturn's relatively young rings also challenges assumptions about the stability and longevity of planetary ring systems, offering clues about the formation of other ring planets in our galaxy. 108. Uranus likely once collided violently. Uranus' unusual axial tilt of about 98 degrees suggests it experienced a massive collision early in its history. This impact likely knocked the planet onto its side, dramatically affecting its rotation, internal structure, and distribution of moons and rings. The violent collision may also explain Uranus' relatively low internal heat emission and unusual magnetic field orientation, which is tilted and offset from the planet's center. Studying Uranus' tilt and internal properties helps scientists understand the dynamics of planetary formation, giant impacts, and the evolution of ice giants. Simulations of such collisions reveal how enormous impacts can alter rotation, tilt, and even atmospheric circulation. Uranus' likely violent past demonstrates that planetary histories can be shaped by catastrophic events, influencing long-term structure, climate, and satellite systems. Investigating this scenario offers insight into exoplanet formation, where collisions may be common, and helps explain why Uranus differs so dramatically from its neighbor Neptune despite similar size and composition. 109. Neptune's storms appear and vanish. Neptune experiences dynamic, short-lived storms that appear and disappear across its atmosphere. These storms, including dark vortices and bright cloud formations, are driven by high-speed winds exceeding 2,000 km per hour and internal heat escaping from the planet's interior. Despite being far from the Sun, Neptune radiates more energy than it receives, fueling dramatic weather patterns. Observations from Voyager 2 and Hubble reveal storms forming, migrating, and dissipating over months or years. Studying Neptune's transient weather helps scientists understand atmospheric dynamics under extreme conditions, including the role of internal heat, wind shear, and planetary rotation. The formation and disappearance of storms demonstrate how ice giants maintain active meteorology without strong solar input. Understanding Neptune's storm behavior also provides insight into comparative planetology, modeling exoplanetary atmospheres, and the interaction between internal energy and visible atmospheric features. Neptune's ever-changing storms reveal a complex and energetic environment far beyond the reach of Earth's weather systems, showing the diversity of planetary climates in our solar system. 110. Pluto's orbit sometimes crosses Neptune. Pluto's highly elliptical orbit occasionally crosses that of Neptune, although the two bodies never collide due to a stable 3:2 orbital resonance. This resonance ensures that Pluto completes 2 orbits for every 3 of Neptune, maintaining a safe gravitational dance. The orbit is inclined relative to the planets, further reducing collision risk. Pluto's orbital path demonstrates the complexity of solar system dynamics, including resonance, eccentricity, and long-term stability of small icy bodies. Studying Pluto's orbit helps scientists understand Kuiper Belt objects, the evolution of distant solar system bodies, and gravitational interactions that shape orbital stability. Observations and simulations reveal how orbital resonances prevent collisions, distribute objects in belts, and influence the migration of giant planets during the solar system's early history. Pluto's orbit crossing Neptune is a fascinating example of celestial mechanics, resonance, and the delicate gravitational balance that maintains order among chaotic small bodies in the outer solar system. 111. Solar flares disrupt Earth communications. Solar flares are sudden, intense bursts of radiation from the Sun's surface that release massive energy into space. When directed toward Earth, these flares can disrupt radio communications, satellite operations, and GPS signals. High-energy particles from flares interact with Earth's magnetosphere, creating geomagnetic storms that can also affect power grids. Solar flares vary in intensity and often accompany coronal mass ejections, which eject plasma into space. Understanding solar flares is crucial for predicting space weather and protecting technology-dependent infrastructure. Observations from satellites like SOHO and SDO monitor flares in real time, allowing forecasters to issue warnings. Flares also contribute to auroral activity, creating spectacular light displays in polar regions. Studying these events helps scientists understand solar magnetic activity, the mechanisms behind energy release, and the impact on planetary environments. Solar flares illustrate the Sun's dynamic nature and the importance of monitoring its influence on Earth and the broader solar system. 112. The Sun will become red giant. In about 5 billion years, the Sun will exhaust hydrogen in its core and expand into a red giant, dramatically increasing in size and luminosity. Its outer layers will engulf the inner planets, possibly including Mercury, Venus, and Earth. During this phase, the Sun's surface temperature will decrease, giving it a reddish appearance. The red giant stage marks the end of the Sun's main sequence life, after which it will shed outer layers to form a planetary nebula, leaving behind a dense white dwarf. Understanding the Sun's evolution informs stellar astrophysics, the life cycles of stars, and the ultimate fate of planets in solar systems. Observing red giants in distant star systems provides models for predicting changes in luminosity, radius, and planetary effects. The Sun's transformation into a red giant demonstrates the long-term evolution of stars like our own, highlighting the transient nature of habitable conditions on planets and the eventual reshaping of the solar system. 113. Mercury's craters remain well preserved. Mercury's surface is densely covered with impact craters that have remained largely unchanged due to the planet's lack of atmosphere, weather, or tectonic activity. These craters record billions of years of collisions with asteroids and comets, offering a window into the early solar system. Some craters feature bright rays of ejected material, while others are ancient and eroded by micrometeorite impacts. Studying Mercury's craters helps scientists understand impact rates, surface age, and planetary formation processes. Unlike Earth or Venus, Mercury's minimal geological activity preserves these features exceptionally well. Crater analysis also reveals subsurface composition, the distribution of volatiles, and the effects of solar radiation on surface materials. By examining these well-preserved craters, researchers gain insight into planetary evolution, impact mechanics, and the history of bombardment that shaped terrestrial planets. Mercury's cratered surface is a natural record of cosmic events spanning billions of years. 114. Venus has volcanic surface features. Venus' surface is dotted with volcanic plains, lava flows, and large shield volcanoes, suggesting extensive volcanic activity in the planet's past and possibly ongoing eruptions. Radar mapping reveals features such as coronae, pancake domes, and rift valleys formed by volcanic and tectonic processes. Volcanism has contributed to Venus' dense atmosphere by releasing carbon dioxide and sulfur compounds. Studying these features helps scientists understand planetary resurfacing, heat release mechanisms, and greenhouse gas accumulation. Venus' volcanic activity may also influence supertating winds and cloud dynamics. Evidence of recent or active volcanism would provide critical insight into the planet's interior, surface evolution, and atmospheric chemistry. By comparing Venusian volcanism to Earth's, researchers gain perspective on how terrestrial planets evolve under extreme temperatures, pressures, and atmospheric conditions. Volcanic features make Venus a natural laboratory for studying the interplay between geology and atmosphere on rocky worlds. 115. Earth has a molten core. Earth's core is composed of a solid inner core and a molten outer core made of iron and nickel. The movement of molten material generates Earth's magnetic field through the geodynamo process, protecting life from solar and cosmic radiation. The core also influences plate tectonics, mantle convection, and heat transfer to the surface. Studying the core provides insight into Earth's formation, thermal evolution, and magnetic history. Seismic waves, magnetic studies, and laboratory simulations help scientists model core composition, temperature, and dynamics. The molten outer core plays a critical role in generating auroras, guiding navigation, and maintaining conditions necessary for life. Understanding Earth's core also informs comparisons with other planets, explaining why some have magnetic fields while others, like Venus and Mars, do not. The molten core demonstrates the dynamic internal processes that shape Earth's surface, atmosphere, and habitability over billions of years. 116. Mars may have ancient shorelines. Geological evidence on Mars suggests that the planet once hosted large bodies of liquid water, forming ancient shorelines, lake beds, and river valleys. These features indicate that Mars had a warmer, wetter climate billions of years ago, possibly supporting microbial life. Rovers and orbiters have identified sedimentary layers, delta formations, and mineral deposits consistent with past water activity. Studying these ancient shorelines helps scientists understand Mars' climate evolution, water cycles, and habitability potential. Water-related features provide insight into the history of atmospheric loss, surface erosion, and chemical interactions. Discovering signs of past oceans or lakes guides the search for life, both extinct and potentially extant in underground reservoirs. Mars' ancient shorelines reveal that the planet's environmental conditions were once more Earth-like, demonstrating how planetary climates can change drastically over geological timescales. These features serve as key targets for exploration and sampling in future missions. 117. Jupiter's Ganymede has a magnetic field. Ganymede, Jupiter's largest moon, possesses its own intrinsic magnetic field, a rare feature for a moon. This magnetic field is generated by a convecting liquid iron or iron sulfide core and interacts with Jupiter's powerful magnetosphere. Ganymede's magnetic environment creates auroras, affects charged particles, and provides insight into its internal structure and thermal evolution. Studying Ganymede helps scientists understand how moons can develop magnetic fields, the role of internal heat, and the potential for subsurface oceans. Its magnetosphere also offers clues about space weather interactions and the habitability of icy moons. Observations from spacecraft such as Galileo reveal complex interactions between Ganymede, Jupiter, and surrounding plasma, demonstrating the moon's dynamic electromagnetic environment. Ganymede's magnetic field makes it unique among moons, showing that even small bodies can sustain geodynamo processes similar to those on planets. 118. Saturn's Titan resembles early Earth. Titan, Saturn's largest moon, has a thick nitrogen-rich atmosphere, hydrocarbon lakes, and surface rivers, resembling early Earth before life emerged. Methane cycles on Titan create precipitation, rivers, and lakes, while the atmosphere protects the surface from radiation. Studying Titan helps scientists understand prebiotic chemistry, climate systems, and the conditions for life on other worlds. Complex organic molecules have been detected, indicating chemical processes similar to those that may have led to life on Earth. Cassini and Huygens missions provided detailed observations of Titan's landscape, dunes, and lakes. Titan's resemblance to early Earth makes it a valuable target for astrobiology, exploring the origins of life and understanding planetary evolution. Its thick atmosphere, liquid hydrocarbon systems, and active weather cycles illustrate how conditions on moons can mimic early planetary environments, offering insight into potential habitable niches beyond Earth. 119. Uranus moons are icy worlds. Uranus moons are primarily composed of ice and rock, featuring cratered surfaces, frozen plains, and evidence of past geological activity. Moons like Miranda exhibit cliffs, ridges, and signs of tectonics, while others are heavily cratered, showing ancient surfaces. These icy worlds may harbor subsurface oceans, particularly on larger moons, potentially creating environments suitable for exotic forms of life. Studying Uranus moons provides insight into moon formation, tidal heating, and the evolution of ice-rich bodies. Their composition helps scientists understand the diversity of outer solar system satellites and compare them with moons of Jupiter and Saturn. Observations of surface features, orbits, and internal structures reveal interactions with Uranus' magnetic field and gravitational influences, demonstrating complex planetary moon systems. Uranus' icy moons highlight the diversity of planetary satellites and their potential for hidden, dynamic processes beneath frozen surfaces. 120. Neptune's moon Triton may be captured. Triton, Neptune's largest moon, is unique because it orbits in a retrograde direction, suggesting it was captured from the Kuiper Belt rather than forming alongside Neptune. Its orbit and geological features indicate past tidal heating, cryovolcanism, and active surface reshaping. Triton has nitrogen geysers, icy plains, and a thin atmosphere, hinting at internal energy sources and a dynamic past. Studying Triton provides insight into moon capture mechanics, orbital evolution, and the effects of tidal forces on icy bodies. Understanding its origin helps scientists explore the history of the outer solar system, the migration of Kuiper Belt objects, and interactions with Neptune's gravity. Triton's unusual characteristics make it a natural laboratory for studying captured satellites, cryovolcanism, and exotic planetary systems far from the Sunday 121. Pluto's sky glows faint blue. Pluto's tenuous atmosphere scatters sunlight to create a faint blue glow above its surface, particularly visible during sunrise or sunset. Composed primarily of nitrogen with traces of methane and carbon monoxide, this thin atmosphere allows sunlight to interact with particles, producing a subtle bluish hue. Observations from New Horizons revealed the layered haze extending hundreds of kilometers, giving Pluto a delicate, ethereal appearance. The haze forms through photochemical reactions triggered by solar radiation, creating complex hydrocarbons and aerosols. Studying Pluto's sky provides insight into atmospheric chemistry on small, cold worlds and the processes that shape dwarf planet environments. The faint blue glow is influenced by atmospheric density, particle size, and light scattering, similar to Earth's sky but under far colder, thinner conditions. Understanding Pluto's atmospheric haze helps scientists model the evolution of distant icy bodies, surface-atmosphere interactions, and potential climate cycles over time. Pluto's glowing sky demonstrates that even tiny, remote worlds can possess dynamic atmospheres that interact with sunlight in visually striking ways. 122. Solar radiation influences planet atmospheres. Solar radiation drives the climate, weather, and chemistry of planetary atmospheres across the solar system. High-energy photons interact with gases, creating photochemical reactions, auroras, and ionized layers. On Earth, solar radiation powers weather systems, the water cycle, and photosynthesis, while also shaping the ozone layer. On Venus and Mars, it contributes to greenhouse warming, atmospheric escape, and chemical reactions altering surface and atmospheric composition. Solar radiation can strip light elements from thin atmospheres, as seen on Mercury and Mars, influencing long-term evolution. It also impacts habitability by controlling surface temperatures and energy input. Studying radiation effects on different planets helps scientists understand climate processes, atmospheric retention, and planetary evolution. Solar radiation varies with solar cycles, flares, and coronal mass ejections, which can induce geomagnetic storms, disrupt satellites, and alter space weather environments. By comparing these effects across planets, researchers gain insight into atmospheric stability, planetary protection mechanisms, and how exoplanet atmospheres may respond to stellar radiation. 123. The Sun consumes fuel gradually. The Sun generates energy through nuclear fusion, converting hydrogen into helium in its core. This process releases immense energy that powers sunlight, heat, and solar winds. The consumption of hydrogen occurs gradually over billions of years, maintaining a stable luminosity during the Sun's main sequence life. As fuel is used, the Sun's core slowly contracts and heats up, ensuring fusion continues. Over time, the changing core composition affects solar output, eventually leading to its evolution into a red giant. Understanding the Sun's gradual fuel consumption helps scientists predict its life cycle, energy output, and the long-term habitability of planets. Solar energy drives climate, weather, and photosynthesis on Earth, sustaining life. Monitoring solar fusion processes through spectroscopy, helioseismology, and neutrino detection provides insight into stellar physics, energy generation, and the delicate balance maintaining stability in stars like the Sun. The slow consumption of fuel ensures billions of years of energy for the solar system, making life on Earth possible. 124. Mercury shows chaotic rotation. Mercury's rotation is unusual due to gravitational interactions with the Sun, exhibiting a 3:2 spin-orbit resonance, where it rotates 3 times for every 2 orbits. This creates a chaotic rotation pattern in longitude, causing extreme temperature variations on the surface. Mercury's rotation is influenced by its elongated orbit, tidal forces, and its partially molten core. Understanding Mercury's rotation helps scientists study planetary dynamics, spin-orbit resonances, and tidal heating effects. The chaotic rotation affects solar exposure, crater temperatures, and volatile stability in polar regions. Studying Mercury's rotational behavior provides insight into the evolution of small, rocky planets near their stars and the complex interactions between rotation, orbit, and internal structure. Observations from spacecraft such as Messenger allow researchers to model Mercury's rotation, surface heating, and long-term stability. Mercury's unique rotational pattern demonstrates how planetary spins can be influenced by gravitational forces, producing extreme environmental conditions on its surface. 125. Venus Day exceeds its year. Venus rotates on its axis extremely slowly, completing one rotation every 243 Earth days, while it orbits the Sun in only 225 Earth days. This means a Venusian day is longer than its year. The planet's retrograde rotation causes the Sun to rise in the west and set in the east. The slow spin contributes to extreme atmospheric dynamics, including superrotating winds and uniform surface temperatures. Scientists believe Venus' unusual rotation may result from massive collisions or tidal interactions with the Sun. Understanding Venus' slow rotation helps model planetary climates, atmospheric circulation, and the evolution of terrestrial planets. Its rotation influences cloud movement, heat distribution, and wind patterns, contributing to the planet's extreme greenhouse conditions. Venus Day exceeding its year is a striking example of how planetary rotation can vary dramatically, shaping the planet's environment and long-term evolution. 126. Earth orbits at perfect distance. Earth occupies the habitable zone of the solar system, orbiting the Sun at an ideal distance to maintain liquid water on its surface. This distance allows a stable climate suitable for life, balancing solar energy absorption and planetary cooling. Slight variations in orbit, tilt, and precession influence seasons, climate cycles, and long-term environmental changes. Earth's orbital position ensures moderate temperatures, preventing runaway greenhouse or icehouse conditions. Studying Earth's orbit and its effect on habitability helps scientists understand climate evolution, planetary stability, and the search for life on exoplanets. Earth's distance from the Sun, combined with its atmosphere and magnetic field, creates the precise conditions necessary for oceans, ecosystems, and complex life to flourish. The planet's orbit demonstrates the delicate balance required for long-term habitability and the role of orbital mechanics in shaping planetary environments across the galaxy. 127. Mars' weak magnetism exposes surface. Mars has a very weak magnetic field compared to Earth, with only localized crustal magnetism. This exposes the planet's surface to solar wind and cosmic radiation, contributing to atmospheric erosion and the loss of water over billions of years. Without a strong global magnetosphere, charged particles strip away lighter molecules, shaping Mars' thin, carbon dioxide-rich atmosphere. Studying Mars' weak magnetism helps scientists understand planetary evolution, habitability, and how magnetic fields protect atmospheres. The weak field also influences radiation levels for future human exploration, surface chemistry, and potential microbial survival. Mars' exposed surface provides insight into how terrestrial planets can lose magnetic protection, the role of internal heat in sustaining magnetospheres, and the long-term effects on climate and atmospheric retention. Observations from orbiters and landers allow researchers to study crustal magnetism, atmospheric loss, and the planet's dynamic history. 128. Jupiter formed early in system. Jupiter, the largest planet, formed early in the solar system's history, quickly accumulating gas and solids to become a massive gas giant. Its formation shaped the orbital evolution of other planets, influenced asteroid belt distribution, and contributed to the migration of smaller bodies. Jupiter's gravity protected inner planets from excessive comet bombardment while also redirecting some objects toward the inner solar system. Studying Jupiter's early formation provides insight into planetary accretion, gas giant development, and the role of giant planets in shaping planetary systems. Observations of its composition, moons, and orbital characteristics reveal the timing, dynamics, and processes that allowed Jupiter to dominate the outer solar system. Its early formation demonstrates the importance of massive planets in determining the architecture, stability, and evolution of planetary systems. 129. Saturn's core may be diffuse. Saturn's interior likely contains a diffuse core composed of rock, ice, and metallic hydrogen, unlike a sharply defined central core. This diffuse structure contributes to Saturn's lower density, rapid rotation, and gravitational field variations. Internal processes, including helium rain and heat transport, shape the planet's energy emission and influence its magnetic field. Understanding Saturn's core helps scientists model giant planet interiors, formation, and evolution. Observations from Cassini and theoretical models suggest that the core may gradually blend into surrounding layers, affecting thermal dynamics and long-term evolution. Studying Saturn's diffuse core provides insight into the diversity of planetary structures and the internal mechanisms governing giant planets. 130. Uranus barely emits internal heat. Uranus emits almost no excess heat compared to the energy it receives from the Sun, an unusual trait for an ice giant. This may result from a past massive collision that redistributed internal heat or a layered structure preventing efficient heat transport. The low internal heat affects atmospheric convection, wind speeds, and weather systems. Studying Uranus' thermal emission helps scientists understand planetary cooling, interior dynamics, and energy balance in ice giants. Observations suggest the planet's interior behaves differently than Neptune, despite similar composition, highlighting the diversity of planetary thermal evolution. Understanding Uranus' heat emission is key for modeling ice giant atmospheres, magnetic fields, and potential internal oceans. 131. Neptune formed from icy material. Neptune is an ice giant primarily composed of water, ammonia, methane ices, and rock, forming in the outer solar system where cold conditions allowed volatile materials to condense. Its icy composition differentiates it from gas giants like Jupiter and Saturn, influencing its density, magnetic field, and atmospheric dynamics. Studying Neptune's formation provides insight into the accretion of volatile-rich planets, migration, and early solar system processes. Icy materials contribute to internal heat, cloud formation, and weather systems. Observations of Neptune and its moons offer clues about how ice-rich planets evolve, retain heat, and generate magnetic fields under extreme conditions. Neptune's icy composition serves as a model for understanding similar exoplanets in cold, distant orbits around other stars. 132. Pluto's temperature drops extremely low. Pluto experiences extreme cold, with surface temperatures averaging around -225 degrees Celsius, due to its distance from the Sun and thin nitrogen-rich atmosphere. These frigid conditions cause nitrogen, methane, and carbon monoxide to freeze, forming glacier, ice plains, and seasonal frost layers. Temperature variations influence Pluto's surface geology, atmosphere, and volatile cycles. The extreme cold allows for preservation of ancient ices and provides a unique environment for studying cryogenic processes. Observations from New Horizons revealed how temperature-driven sublimation and deposition shape surface features. Studying Pluto's low temperatures helps scientists understand outer solar system bodies, dwarf planets, and icy worlds in the Kuiper Belt. The extreme cold demonstrates how distance from the Sun, atmosphere, and surface composition combine to create harsh, dynamic environments beyond the main planets. 133. Solar System has dwarf planets. The Solar System contains numerous dwarf planets, including Pluto, Eris, Haumea, and Makemake, which are celestial bodies that orbit the Sun but lack the mass to clear their orbits of debris. These bodies inhabit regions such as the Kuiper Belt and scattered disk, offering insight into planetary formation and evolution. Studying dwarf planets helps scientists understand the distribution of mass, orbital dynamics, and surface compositions beyond the main planets. Many dwarf planets have icy surfaces, thin atmospheres, and unique geological features, revealing diverse processes in low-gravity, cold environments. Observations of their orbits and interactions also shed light on resonance, migration, and collisional history in the outer solar system. Dwarf planets represent a distinct category of objects that challenge traditional definitions of planets and expand our understanding of the solar system structure. 134. Many asteroids are leftover material. Asteroids are remnants of the early solar system, composed of rock, metal, and organic compounds that never coalesced into planets. Most reside in the asteroid belt between Mars and Jupiter, with others scattered throughout the inner and outer solar system. Studying asteroids provides clues about planetary formation, chemical composition, and the processes that shaped the early solar system. Collisions among asteroids create smaller fragments, meteorites, and dust that influence planetary surfaces and atmospheres. Some asteroids may contain water or organic materials, offering insight into the building blocks of life. Observing asteroid orbits and composition helps predict potential Earth impacts and guides exploration missions. These ancient leftover materials serve as natural time capsules, preserving information about the solar system's origin, evolution, and the diversity of small celestial bodies. 135. Comets contain primordial solar ingredients. Comets are icy bodies composed of water, carbon dioxide, methane, ammonia, and dust, preserving primordial ingredients from the solar system's formation. Originating from the Kuiper Belt or Oort Cloud, comets provide insight into early solar chemistry, planetary formation, and volatile distribution. When approaching the Sun, comets develop glowing comas and tails as ices sublimate, revealing composition and structure. Studying comets helps scientists understand the delivery of water and organic molecules to early Earth, possibly contributing to life. Missions like Rosetta and Deep Impact analyzed cometary material, revealing complex organics, isotopic ratios, and dust particle composition. Comets act as frozen time capsules, preserving conditions from over 4.5 billion years ago. Observing their orbits, interactions, and activity provides critical data on the evolution of small bodies, the dynamics of the outer solar system, and the processes that shaped planetary systems. Comets remain essential for understanding the primordial ingredients that built planets and life-supporting environments. 136. Meteoroids continually enter Earth's atmosphere. Every day, countless meteoroids from space enter Earth's atmosphere, most burning up due to friction and producing brief streaks of light called meteors. Larger meteoroids may survive the descent, striking the surface as meteorites. These incoming space rocks originate from the asteroid belt, comets, or leftover planetary formation debris. Meteoroid impacts provide scientists with material from the early solar system, including minerals, metals, and sometimes organic compounds. Observing meteors helps understand the distribution, size, and composition of these small bodies. Some meteoroids are so small they disintegrate harmlessly, while others can create craters or influence atmospheric chemistry. Meteor showers, resulting from Earth-crossing cometary debris trails, produce spectacular displays visible from the surface. Studying meteoroids also informs planetary defense strategies, tracking potentially hazardous objects that could impact Earth. Meteoroids continually entering the atmosphere remind us that Earth exists within a dynamic, constantly interacting cosmic environment and that space is full of material that has persisted for billions of years. 137. The Sun's core reaches extreme temperatures. The Sun's core reaches temperatures around 15 million degrees Celsius, hot enough to sustain nuclear fusion. Hydrogen nuclei combine to form helium, releasing immense energy that powers sunlight, solar wind, and heat throughout the solar system. Extreme pressure and density in the core allow fusion to occur despite repelling forces between atomic nuclei. Energy produced in the core slowly radiates outward, taking thousands of years to reach the surface. The core's intense heat and pressure also influence solar structure, convection, and magnetic activity. Understanding core conditions provides insight into stellar life cycles, energy generation, and the evolution of stars like our Sun. Solar neutrinos, emitted during fusion, provide direct evidence of nuclear reactions. Studying these extreme temperatures helps scientists model how stars sustain life-giving energy, how fusion operates under extreme conditions, and how internal processes drive solar phenomena such as flares, sunspots, and coronal mass ejections. The Sun's core illustrates the power and complexity behind the energy that supports life on Earth and shapes the entire solar system. 138. Mercury's exosphere is extremely thin. Mercury lacks a true atmosphere, possessing instead a tenuous exosphere composed of atoms ejected from its surface by solar radiation, micrometeoroid impacts, and charged particle interactions. This exosphere contains hydrogen, helium, sodium, potassium, and other trace elements, but it is far too thin to support weather or retain heat. Mercury's weak gravity and proximity to the Sun allow particles to escape into space quickly. Studying the exosphere provides insight into surface composition, solar-wind interactions, and atmospheric evolution on small, rocky planets. Despite its thinness, Mercury's exosphere produces observable phenomena such as sodium tails and auroral-like effects. Understanding Mercury's exosphere helps scientists model atmospheric loss, surface exosphere coupling, and the behavior of planetary bodies with minimal atmospheres. Its fragile exosphere demonstrates how extreme conditions near the Sun can strip or prevent the accumulation of gases, offering a contrast to planets with dense, protective atmospheres like Venus and Earth. Mercury's exosphere is a dynamic boundary between the planet and space, reflecting ongoing interactions with solar radiation and micrometeoroids. 139. Venus surface pressure crushes metal. Venus' surface pressure is approximately 92 times that of Earth, enough to crush metal and create extreme environmental conditions. The dense atmosphere, composed mostly of carbon dioxide, traps heat through a runaway greenhouse effect, producing surface temperatures over 460 degrees Celsius. The high pressure and heat make Venus' surface hostile to spacecraft, causing early landers to fail within hours. Studying these conditions helps scientists understand greenhouse warming, atmospheric dynamics, and planetary evolution. The crushing pressure also influences geology, volcanic activity, and potential interactions between surface and atmosphere. Observations from radar mapping reveal mountains, plains, and volcanic formations shaped under immense pressure. Venus' extreme surface conditions serve as a natural laboratory for understanding the limits of habitability, the effects of thick atmospheres, and the challenges faced by future missions. The planet's crushing pressure illustrates how planetary atmospheres can dramatically shape surface environments and demonstrates the importance of studying other worlds to understand climate extremes in the solar system. 140. Earth's climate allows diverse ecosystems. Earth's climate, influenced by solar energy, atmospheric composition, ocean currents, and tilt, creates conditions suitable for a wide variety of ecosystems. From tropical rainforests to polar tundras, climate regulates temperature, precipitation, and seasonal cycles essential for life. Climate stability allows complex ecosystems to thrive, supporting biodiversity and human civilization. The interaction between atmosphere, oceans, and land shapes habitats, migration patterns, and ecological processes. Studying Earth's climate helps scientists predict environmental changes, understand climate feedbacks, and protect ecosystems from threats such as global warming. Variations in climate over geological time influence species evolution, adaptation, and extinction. Earth's climate also maintains water in liquid form, stabilizes temperature ranges, and distributes energy across the planet. Understanding the mechanisms behind Earth's climate, including solar radiation, greenhouse gases, and ocean-atmosphere interactions, is critical for predicting future changes. The planet's climate enables life to flourish in diverse forms, making Earth uniquely habitable in the solar system. 141. Mars' thin air prevents liquid water. Mars has a thin atmosphere, mostly carbon dioxide, which is insufficient to maintain liquid water on the surface for extended periods. Low pressure causes water to rapidly evaporate or freeze, limiting conditions for life as we know it. This thin atmosphere also offers little protection from solar radiation and contributes to extreme temperature swings. Evidence of past water activity, such as dried riverbeds and ancient lake deposits, suggests that Mars once had a thicker atmosphere. Studying Mars' thin air helps scientists understand atmospheric loss, climate evolution, and the challenges for potential human exploration. The thin atmosphere affects dust storms, weather patterns, and surface conditions, shaping the planet's geology and habitability potential. Understanding how Mars' atmosphere became so tenuous provides insight into the evolution of terrestrial planets and the delicate balance required for sustaining surface water and life. 142. Jupiter's rotation is extremely fast. Jupiter rotates once every approximately 10 hours, making it the fastest spinning planet in the solar system. This rapid rotation flattens the planet at the poles and creates strong equatorial bulges. Fast rotation drives Jupiter's intense atmospheric circulation, producing bands of clouds, storms, and the Great Red Spot. The rotation also influences the planet's powerful magnetic field and internal dynamics. Studying Jupiter's rapid spin helps scientists understand gas giant formation, angular momentum distribution, and the interaction between rotation and atmospheric phenomena. Fast rotation contributes to differential wind speeds, turbulence, and complex weather patterns observed across the planet. It also shapes the orbits of moons and ring systems, affecting gravitational interactions. Jupiter's extreme rotation demonstrates how planetary spin influences structure, magnetism, and weather on massive gas giants. 143. Saturn's rings vary by composition. Saturn's rings are composed of ice, rock, and dust, with variations in particle size, density, and composition across the system. The rings contain countless particles from tiny grains to large boulders, forming gaps, waves, and structures shaped by Saturn's moons. Differences in brightness and color reveal compositional diversity, with water ice dominating and other materials contributing darker regions. The rings are dynamic, constantly evolving due to collisions, gravitational interactions, and orbital resonances. Studying Saturn's rings provides insight into planetary ring dynamics, moon formation, and the evolution of circumplanetary disks. The rings' diversity reflects both the processes that created them and ongoing interactions, offering a natural laboratory for understanding debris behavior in space. Observations from Cassini revealed complex structures such as the Cassini division, spokes, and propeller features. Saturn's rings highlight the beauty and complexity of planetary ring systems and their ever-changing nature. 144. Uranus' axis tilt is dramatic. Uranus has an extreme axial tilt of about 98 degrees, causing it to rotate almost on its side. This unique tilt produces unusual seasonal variations, with each pole experiencing 42 years of continuous sunlight or darkness. The dramatic tilt may result from a massive collision during Uranus' early history. Its orientation affects atmospheric circulation, wind patterns, and internal heat distribution. Studying Uranus' tilt helps scientists understand planetary formation, the effects of impacts, and the behavior of ice giants. The axial tilt also influences the visibility and orientation of its rings and moons, contributing to complex orbital interactions. Uranus' extreme tilt provides a natural laboratory for exploring how catastrophic events can reshape planetary rotation and climate, offering insights into the diversity of planetary dynamics in the solar system. 145. Neptune storms exceed Earth's hurricanes. Neptune experiences storms far more powerful than hurricanes on Earth, with winds exceeding 2,000 kilometers per hour. These storms, including dark vortices and bright cloud systems, are fueled by internal heat, rapid rotation, and atmospheric convection. Despite its distance from the Sun, Neptune radiates more energy than it receives, driving active weather. Studying Neptune storms helps scientists understand atmospheric dynamics under extreme conditions, including wind shear, convection, and vortex formation. Observations from Voyager 2 and Hubble show storms forming, moving, and dissipating over months. Neptune's powerful storms highlight the differences between gas and ice giant meteorology compared to Earth, offering insight into the behavior of atmospheres in low-temperature, high-wind environments. Understanding these storms improves models of exoplanetary weather and extreme atmospheric processes. 146. Pluto's mountains are made of ice. Pluto's mountains, or mantes, are composed primarily of water ice, forming rugged peaks hundreds of meters high. Ice behaves like rock under Pluto's extremely cold conditions, creating stable mountain ranges. These formations result from tectonic processes, cryovolcanism, or ancient collisions. Studying icy mountains helps scientists understand geological activity, surface evolution, and volatile transport on dwarf planets. Observations from New Horizons revealed mountains adjacent to plains, craters, and glacial regions, indicating dynamic surface interactions. Pluto's icy mountains demonstrate that even small, cold worlds can sustain geological processes, offering insight into the behavior of ices under extreme low temperatures and low gravity. 147. Kuiper Belt contains icy bodies. The Kuiper Belt is a vast region beyond Neptune populated with icy bodies, dwarf planets, and remnants of the early solar system. Objects like Pluto, Haumea, and Makemake reside in this belt, composed mainly of ices and rock. Studying the Kuiper Belt helps scientists understand planetary formation, orbital dynamics, and the distribution of primordial material. Collisions and gravitational interactions shape the region's population, providing insight into the solar system's outer edge. Kuiper Belt objects are key targets for understanding how icy bodies evolve over billions of years and their potential role in delivering volatiles to inner planets. Observing these distant objects sheds light on the structure, composition, and history of our solar system's periphery. 148. Oort Cloud may hold trillions. The Oort Cloud is a hypothetical, distant spherical shell surrounding the solar system, thought to contain trillions of icy bodies. These objects serve as the source of long-period comets entering the inner solar system. Studying the Oort Cloud helps scientists understand the distribution of primordial material, planetary migration, and the early history of the solar system. Its vast distance makes direct observation difficult, but models and comet tracking provide indirect evidence. The Oort Cloud illustrates the far-reaching influence of the Sun's gravity and the preservation of ancient material from the formation of the solar system. Understanding this cloud provides insight into comet origins, celestial dynamics, and the boundaries of the Sun's gravitational influence. 149. Solar system still evolves slowly. Although billions of years old, the solar system continues to evolve gradually. Planets shift orbits slightly due to gravitational interactions, moons experience tidal effects, and minor bodies collide or drift. Asteroids, comets, and Kuiper Belt objects continue to move and interact, reshaping populations and occasionally sending material into the inner solar system. Planetary atmospheres slowly change through chemical reactions, escape, and solar radiation. Even distant regions like the Oort Cloud are influenced by passing stars and galactic tides. Studying these slow evolutionary processes helps scientists understand planetary stability, orbital dynamics, and long-term changes across billions of years. The solar system's evolution is a reminder that even seemingly static celestial systems are dynamic over geological timescales, with subtle changes shaping the future architecture of planets, moons, and small bodies. 150. The Sun will someday fade. In the distant future, the Sun will gradually exhaust its nuclear fuel, evolving into a red giant before shedding its outer layers to form a planetary nebula. The remaining core will become a white dwarf, slowly cooling over billions of years. This process will end the Sun's energy output, profoundly affecting the solar system. Inner planets may be engulfed, and outer planets will experience changing temperatures and conditions. Studying stellar evolution provides insight into the fate of planetary systems, the life cycles of stars, and the long-term evolution of habitable conditions. Observations of distant stars at various stages offer models for predicting the Sun's transformation. The Sun's eventual fading reminds us of the finite lifespan of stars and the transient nature of planetary environments reliant on stellar energy, highlighting the dynamic and ever-changing nature of the cosmos. Thank you for joining this peaceful journey through our solar system. I hope these 150 calming space facts helped you relax, unwind, and drift into a clearer, quieter state of mind. From the scorching surface of Mercury to the icy edges of the Oort Cloud, our cosmic neighborhood is filled with wonders, and tonight, you explored them one gentle step at a time. If this video helped you feel calmer, more grounded, or simply a little more curious, I'd be truly grateful if you liked the video and subscribed to Heavenly Sleep Stories. Your support allows me to create more soothing explorations, bedtime fact lists, and relaxing educational journeys just like this one. Let me know in the comments what topic you'd like to fall asleep to next. Maybe deep ocean mysteries, ancient civilizations, animal facts, psychology facts, or more space wonders. Your ideas inspire the upcoming videos. Until next time, take a deep breath, rest your mind, and remember, the universe is vast, peaceful, and always full of new stories to discover. Sleep well, dream softly, and I'll see you in the next relaxing journey.